Rewind the universe far enough and every star, every atom, even light itself disappears, until physics hits a wall. Scientists call it nothing, but this nothing has rules, energy, and a terrifying question built in. If there was truly nothing before the Big Bang, what was it that exploded? And what, exactly, was there to do the exploding? Some questions don't ask for an answer. They ask what an answer is allowed to mean. At the universe's threshold, even before becomes a suspect word, and nothing stops behaving like empty space. To follow this mystery, we have to do something rare in science and rarer in storytelling: treat ordinary language as evidence. We say nothing as if it were a plain absence, a blank room with the lights turned off. But cosmology is not built on rooms or lights, or even a guaranteed backdrop where events can line up. In the earliest chapters of reality, the stage may be part of the plot. This documentary is a guided descent through our best measurements and our most careful definitions, where imagination is welcome but only on a short leash. We will watch the modern universe expand in reverse, not as a cinematic blast, but as geometry changing its mind. We will meet the sky's oldest photograph, a faint afterglow that still carries the fingerprints of primordial structure. And we will approach a mathematical precipice where our trusted equations begin to contradict themselves. At that edge, the word nothing becomes a boundary marker rather than a description, and every assumption starts to show. Does nothing mean no matter, no energy, no fields, no laws, or no time in which laws could even apply? When physicists speak with confidence about a beginning, are they describing the world or the limits of their models? And when they propose bold bridges across the gap, an early burst of expansion, a vacuum with restless activity, a cosmos that cycles or branches, what would count as proof rather than poetry? We won't pretend the answer is simple, or that mystery is a failure. Instead, we will separate what is observed from what is inferred, and what is inferred from what is merely assumed. Along the way, you'll see why the universe can look exquisitely orderly while being born from uncertainty, and why nothing may be the most demanding idea science has ever tried to define. This is not a hunt for a single sentence that ends the debate. It is an investigation into a frontier where physics becomes philosophy without losing its discipline, and where clarity can be as unsettling as ignorance. By the time we reach the farthest limit our evidence allows, you may find that the deepest surprise isn't what might have been there. It's what the question itself does to space, time, and meaning. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. We begin by dismantling nothing. Then follow expansion and the universe's oldest light back toward the point where physics falters. From there, we test the leading ideas that reach beyond the boundary, without mistaking speculation for discovery. Imagine rewinding everything you know until there is no sky, no stars, no darkness, and no horizon to orient your thoughts. Now remove the stage itself, because space is not a container here, it is part of what we are trying to erase. Remove time, because without change, there is no before or after, and no rhythm for a clock to imitate. Remove matter and energy, because there are no particles to count, no radiation to measure, and no heat to define. Remove cause and effect, because causality needs time to order events, and order needs a sequence to make sense. That instruction sounds simple, yet the mind resists it with pictures that feel unavoidable. We keep imagining an empty room, an endless black, a quiet void, or a cold expanse waiting to be filled. Those are still something, because they assume space to be empty inside, like a box with the contents removed. They assume time to pass while nothing happens, as though nothing can persist for a while. They assume a viewpoint that can wait and watch, even though a viewpoint already implies a location and a moment. This chapter begins with a calm, unsettling claim heard in science and culture, repeated in classrooms, headlines, and late-night conversations. People say there was nothing before the Big Bang, and the phrase lands like a final answer. Yet it hides several different meanings, and it quietly shifts between them as if they were the same. It also hides the limits of what science can responsibly say, because science is strongest when it stays close to what can be tested. In everyday language, nothing means the absence of things, and we use it without much strain. It means no objects, no sound, no light, no activity, and no obvious trace of presence. Even then, the word usually keeps a background intact, like a stage after the actors leave. There is still a place where the absence occurs, and there is still a time during which the absence lasts. In philosophy, nothing can mean absolute non-being, which is a far sharper and stranger target. It means no space, no time, no laws, no possibilities, and no truths, not even the truth that there is nothing. It is not a vacuum and not a blank canvas, because a canvas already has extension and properties. It is not even a condition, because conditions are already something, and they already constrain what could happen. If that is the target, then asking what existed is already confused, because existed presumes the very framework being denied. Physics uses the same word, but it often means something else, and that difference is where many popular misunderstandings begin. In modern cosmology, nothing can mean a vacuum state, which is not the absence of reality. A vacuum is the lowest energy configuration of fields, and fields are the entities our best theories treat as fundamental. It can contain structure, rules, and fluctuations, even when no particles are present for a detector to catch. Quantum field theory deepens the mismatch between words and world, because it changes what we mean by empty. Fields are not optional decorations added to space like fog added to a landscape. They are the basic ingredients that can produce particles as excitations, the way a vibrating string can produce distinct notes. Even in a vacuum, those fields can have non-zero energy and restless uncertainty, because quantum mechanics forbids perfect stillness. So the first task is definitional, not dramatic. When someone says the universe came from nothing, which nothing do they mean? And when do they switch meanings without noticing? Do they mean philosophical non-being, where even laws do not exist and even logic has no footing? Or do they mean a physical vacuum, where laws and fields still operate, and where nothing is really a special kind of something? The central confusion grows because cosmology also stretches the word before, which feels innocent until you examine it closely. Before implies a timeline that already exists, like a road extending past the edge of a map. It implies a clock that can tick in an empty world, even if nothing changes. Yet our best theories suggest time may be part of what began, rather than a backdrop that was always waiting. The Big Bang is often pictured as an explosion in space, a bright blast expanding into surrounding darkness. That image is intuitive, and it is mostly wrong, even though it captures the idea of change and growth. The Big Bang model describes the expansion of space itself from a hot, dense, early state, where distances between points increase as the universe evolves. It does not require a pre-existing emptiness outside the universe, because outside is not part of the model. If space is what expands, then asking what it expands into can be misleading, like asking what the surface of Earth expands into as you walk north. The model does not point to an edge with a surrounding void, and it does not require a center where everything began. It points to distances between points increasing everywhere, so every region sees others receding. The geometry is internal, not a balloon inside a larger room, even if balloons are a useful teaching image. This is already a clue about the word before, because our everyday grammar assumes time as a universal container. If time is tied to the expansion history, then rewinding may approach a boundary where familiar time loses meaning. The question becomes not what happened earlier, but whether earlier is defined in the same way. In that sense, before the Big Bang may be less like yesterday and more like north of the North Pole. Still, the Big Bang is not a single claim, but a framework anchored in evidence, built over decades of observation and refinement. We observe galaxies moving away with a pattern called cosmic expansion, first recognized in the early 20th century as redshifts accumulated. We measure a faint microwave glow that fills the sky, discovered in 1965 and later mapped in exquisite detail. We find light element abundances, hydrogen, helium, and traces of lithium that match a hot early phase predicted by nuclear physics. These observations do not directly show a beginning from nothing, and they do not point a camera at a first moment. They show that the universe was once hotter, denser, and more uniform, and that it has been cooling as it expands. They show that the early universe left fingerprints that still reach us, stretched into microwaves by cosmic growth. They show that our history can be traced back to a young cosmos, even if the earliest pages are torn. Our guiding rule in this documentary is simple and strict, because the subject invites overreach. We follow evidence first, then theories that explain it, and we keep track of what each theory must assume. We separate what is measured from what is hypothesized, even when the hypothesis is elegant. We also track where language misleads us, because words carry hidden assumptions that sound like common sense. Evidence gives us a reliable timeline back to a point, and that point has a specific observational anchor. The cosmic microwave background is a key marker, often called the first light, and it is a snapshot of the universe when it became transparent. It comes from when the universe cooled enough for electrons to bind with nuclei, forming neutral atoms so photons could travel freely. It is not the start, but it is our clearest window, and it fills the sky in every direction. For visuals, imagine the camera drifting through a darkened cosmos until a faint, uniform glow emerges, like heat seen through night vision. Then the glow resolves into tiny temperature variations, mottled like a delicate cosmic weather map. Those small variations, mere tens of microkelvin, are not noise, but the seeds of later structure. They are the imprint of density differences that gravity would amplify into galaxies and clusters. Before that window, the universe was opaque plasma, a hot soup of charged particles scattering light constantly. We infer rather than see, and inference becomes our instrument when direct observation fails. We use particle physics, nuclear reactions, and statistical patterns to reconstruct earlier conditions because those processes leave calculable signatures. Each step backward depends more on theory and less on direct observation, and that is where the mystery thickens. If we keep rewinding, equations lead toward an extreme, and the words we use start to strain. Densities rise, temperatures soar, and space-time curvature grows, meaning gravity itself becomes intensely concentrated. In classical general relativity, the extrapolation can end in a singularity, where quantities diverge and the math stops behaving. A singularity is not a place you could visit, but a sign the theory breaks under conditions it was never meant to handle. When a theory predicts infinite values, it is often warning us, and physics has learned to treat that warning seriously. It says the model is being pushed beyond its domain, like a map that ends at the shoreline. It says new physics is needed, likely quantum gravity, because quantum effects should matter when scales become extremely small and energies extremely high. The singularity is less an answer than a boundary marker, drawn in ink where our understanding fades. This boundary is where the word nothing gets smuggled in, almost as a rhetorical shortcut. If our equations stop, we may be tempted to declare nothing lies beyond, as though a blank page proves the story ends. Yet ignorance is not emptiness, and a breakdown is not a vacuum, because it may hide richer structure. The honest statement is that our map ends, and beyond it we are choosing among possibilities. Cosmology offers candidate extensions, and each changes the meaning of before without always changing the evidence we start from. Inflation proposes a brief era of accelerated expansion very early on, driven by a high-energy state that behaves like repulsive gravity. It can explain why the universe looks so smooth across vast distances, and why space appears nearly flat in its geometry.
It also explains why structure grew from tiny fluctuations, because inflation would stretch microscopic quantum variations into cosmic scales.
Inflation often relies on fields and vacuum-like energy, which returns us to the physical meaning of nothing. A vacuum can drive expansion, seed galaxies, and create particles after it decays into a hotter state, a process sometimes called reheating.
It is not the philosophical void, even if it looks empty to a casual glance, because it still has dynamics and rules.
The deeper question becomes what set that state, and whether inflation itself had a beginning. Quantum ideas push further toward a radical possibility, and they do so by challenging our intuition about time. In some models, the universe can arise from a quantum state without classical time, where time is not a background parameter. The word creation then means a transition in description, not an event inside a pre-existing clock, and that distinction matters. The question becomes how time emerges from deeper rules, and whether the earliest moments are better described as relationships than as instants. Yet we must keep our discipline because speculation can outrun evidence, especially when the visuals are tempting. Some proposals are mathematically elegant but not yet testable, and elegance is not the same as truth.
Others make predictions that could be checked in subtle patterns in the cosmic microwave background,
such as specific statistical signatures. The line between science and story depends on that test, because testability is what keeps imagination accountable. There are also broader possibilities for what lies beyond the Big Bang picture, and they are often discussed as if they were interchangeable.
Cyclic models imagine a universe that bounces through expansions and contractions, replacing a singular beginning with repeated phases.
Multiverse ideas suggest our observable region is one bubble among many, perhaps produced by inflationary processes that do not end everywhere. Quantum gravity approaches suggest space-time itself is emergent from more basic entities, meaning the arena is not fundamental but constructed.
Each proposal tries to answer the same pressure point,
which is both scientific and existential. Why is there something rather than nothing? And why does the universe have a history at all? Why do laws exist? And why these laws, with these constants and these symmetries? But each proposal also risks changing the question into a different one, because nothing is not a single target, and why can mean many things.
The tension at the heart of this chapter is psychological as much as scientific,
because our minds are trained by experience. Every time we picture before, we place events on a timeline, and we imagine waiting for the Big Bang to happen. That mental move may be illegitimate if time begins with the universe, because waiting presumes duration. So we must ask whether our question is deep or whether it is simply misframed.
So we will treat the phrase before the Big Bang as a hypothesis, not a given, and we will watch how it shifts.
Sometimes it will mean earlier than the earliest moment our equations describe, which is a practical scientific boundary. Sometimes it will mean a deeper layer that does not use time at all, where earlier is the wrong tool. Sometimes it will be a category error that reveals our limits, like asking what color a number is.
The stakes are not only cosmic, and they are not only academic,
because the meaning of nothing touches what we think explanations are. If physics can describe a universe emerging from a vacuum state, does that count as something from nothing? Or is it a word game? If the vacuum is governed by laws, where did the laws come from? And what would it even mean for laws to come from anything? At what point does explanation end and description begin?
We also confront a quieter stake, which is humility, and humility is not resignation.
The universe does not owe us intuitive answers, and it does not shape itself to fit human language. Our brains evolved to track objects in space and sequences in time because those skills helped survival. Cosmology asks us to reason beyond those instincts, using math and measurement as prosthetic senses, and accepting that some concepts will feel unnatural.
This opening chapter sets the frame for everything that follows,
and it does so by tightening the relationship between evidence and imagination. We begin with what we can observe, because observation anchors imagination and prevents it from drifting into pure metaphor. We then move to the earliest light, because it is our most direct evidence of the young universe and its physical conditions.
From there, we push toward the edge where current physics fails, because boundaries are where new ideas must earn their place. Then we ask what theories try to replace that failure and what they must assume in order to work. We examine inflation and what it claims to solve, including smoothness, flatness, and the origin of primordial fluctuations. We examine the quantum vacuum and why it is not empty, even when it contains no particles in the usual sense. We examine whether time has a beginning and what that would mean for the word before. Finally, we look beyond the standard story, not to chase fantasy, but to map the serious options with clear labels. Cycles, multiverses, and quantum gravity are not interchangeable answers, even when they share dramatic headlines. They are different ways of redefining the starting point, and they shift the meaning of nothing in different directions. They also carry different predictions and different risks, and we will return to those differences with care. For now, hold on to one careful idea because it will guide everything else. Nothing in physics is rarely nothing in philosophy, and the difference is not a technicality, but a fault line. A vacuum can be a sea of fields with rules and energy, and it can still be the lowest energy state available. And the Big Bang is not an explosion into emptiness, but the expansion of the very arena where emptiness would live. We started by trying to imagine absolute absence, and we found our imagination cheating, smuggling in a background to stand on. We started by asking what existed before, and we found the word before doing hidden work, importing time as an assumption. The mystery is not only what happened at the beginning, but whether beginning is the right concept for the earliest reality. If time is part of the story, then the first chapter may not be once upon a time, but something stranger. Next, we follow the evidence back through an expanding universe to the first light. We will use that ancient glow to build a timeline, and to see exactly where the map turns blank, and where our best questions must change shape. We begin where the evidence is strongest, because the word before becomes slippery almost immediately. When we rewind the universe, we do not watch a blast expand outward into surrounding darkness. We watch distances between galaxies grow as space itself stretches, quietly, relentlessly, and everywhere at once. The Big Bang model starts as a measured pattern in the sky, not a philosophical claim about ultimate origins. It says the universe was once hotter, denser, and more uniform than today, and it says this in the language of data. It does not say we have filmed a first moment, and it does not claim we have proven absolute nothingness. In the 1920s, Edwin Hubble and other astronomers compared galaxy distances with their spectral shifts, using the new power of large telescopes. They spit starlight into rainbows and looked for displaced absorption lines, chemical fingerprints moved from their laboratory positions. Many galaxies showed redshift, meaning their light arrived stretched to longer wavelengths than expected. The simplest reading was recession, with farther galaxies receding faster on average. That relationship became the Hubble-Lemaitre law, linking recession speed to distance in a remarkably orderly pattern. It is not a law of galaxies flying through static space like shrapnel from a single detonation. It is a law of expanding space, where the metric that defines distance changes with time. In modern terms, it is the scale factor evolving, and galaxies mostly ride along with that large-scale flow. Redshift is the key observational handle, because light carries a record of its journey across billions of years. When space expands, the wavelength of a photon expands with it, so the photon's energy drops in a predictable way. That same stretching also dilutes matter and cools radiation, tying expansion to a temperature history we can calculate. The sky becomes a kind of archive, written in wavelengths, intensities, and subtle patterns. Modern surveys extend the early discovery into a precise expansion map,
built from statistics rather than a few heroic measurements. We measure redshifts for millions of galaxies and quasars across cosmic time, and we chart how clustering changes with distance. We also measure distances with multiple methods, so expansion is not inferred from one technique alone. Standard candles, standard rulers, and geometric probes cross-check one another, and the agreement is part of the story. The core idea is simple, and it is easy to mispicture even when the math is clear. Expansion does not require a center, an edge, or an outside, because it is not an explosion into pre-existing emptiness. Every observer sees distant galaxies receding because the space between all large-scale points is growing. The pattern is democratic. No privileged viewpoint is required. A raisin-bread analogy keeps the geometry honest, even if it is imperfect and a little domestic. As the dough rises, every raisin sees other raisins moving away, and the farther raisins separate faster. No raisin sits at the center of the expansion because the expansion is in the dough. The raisins do not need to push through the dough's growth does the work. An expanding grid makes the same point with less kitchen intuition and more geometric clarity. Mark dots on a rubber sheet and stretch it evenly, keeping the stretch uniform across the surface. Each dot sees all other dots recede, and the pattern looks the same from every dot. If you draw rulers on the grid, the rulers themselves lengthen. Distance is what changes. This is why cosmologists say the Big Bang happened everywhere at once, which sounds paradoxical until the picture settles. It is not that matter exploded from one location into surrounding emptiness, leaving a scar in space. It is that the early hot state filled all of space, and space later grew larger. Everywhere is not a destination, it is the starting condition. Rewinding that growth is conceptually clean, even when the physics becomes extreme and our intuitions start to fail. If the universe expands, then earlier times had a smaller scale factor, meaning typical separations were reduced. Smaller scale factor means higher density, higher temperature, and faster interaction rates among particles and radiation. The universe becomes less like a museum of objects and more like a single coupled system. The temperature scaling is one of the simplest guide rails in the rewind, and it is surprisingly powerful. For ordinary radiation, temperature rises as the universe shrinks, roughly inversely with the scale factor, so a smaller universe is a hotter one. The cosmic microwave background is the cooled remainder of that hotter past, stretched and thinned by expansion. Its present temperature, about 2.7 Kelvin, sounds small, yet it is a direct thermometer reading of cosmic history. Density follows its own scaling rules, and those rules shape which ingredients dominate at different times. Matter density increases strongly as volume shrinks, because particles become more crowded in a smaller space. Radiation density increases even faster, because photon energy rises as wavelengths shorten, while the number density also increases. That extra factor makes radiation dominate the earliest eras, even if matter dominates today. That difference matters because the early universe was radiation dominated, and radiation controlled the expansion rate more than matter did. In that era, the pressure of radiation and the energy density of relativistic particles shaped how quickly the scale factor evolved. The expansion history is therefore a physical clock, set by what filled the universe at each stage. When we say time in the early universe, we often mean temperature, because temperature tracks the clock so reliably. The evidence for this hot, dense past does not rest on one pillar, and it does not depend on a single clever interpretation. It rests on three linked observations that reinforce each other, like independent witnesses describing the same event. Galaxy redshifts show expansion. Light element abundances show early nuclear cooking, and the microwave background shows leftover heat. Each one points backward, and together they lock into a coherent timeline. The second pillar is primordial element abundances, predicted by Big Bang nucleosynthesis with a precision that still feels audacious. In the first minutes, the universe was hot enough for nuclear reactions, but it was also expanding fast enough to end them. Those reactions produced helium and deuterium in amounts that depend on density and expansion rate, and they are sensitive to the number of light particle species. In plain terms, the early universe left behind a chemical signature that later stars could not easily erase. When astronomers measure helium in old, low metallicity gas, the numbers match the early universe calculations within small uncertainties. Deuterium is especially sensitive because it is easily destroyed inside stars and therefore preserves a fragile memory of its birth. Its observed abundance is a tight constraint, and it acts like a cosmic barometer for ordinary matter. Lithium is complicated, and its mismatch is a known puzzle, not a collapse. More like a loose thread than a torn fabric. The third pillar is the cosmic microwave background, the most direct relic of the young universe that we can measure with exquisite fidelity. It is a nearly uniform bath of microwaves coming from every direction, so pervasive that it fills the space between galaxies. Its spectrum is an almost perfect blackbody, which is hard to fake with later astrophysics. A blackbody curve is what you expect when matter and radiation were once in near thermal equilibrium, sharing energy efficiently. The microwave background also carries tiny anisotropies, temperature variations at the level of tens of microkelvin across the sky. Those variations encode early density differences, and they are mapped as a faint mottling, like a cosmic weather pattern frozen in time. They match the seed pattern needed for galaxies to form later, after gravity had billions of years to amplify small contrasts. They also match the acoustic physics of a plasma, where gravity and pressure competed and left behind a characteristic scale. These pillars do not prove a metaphysical beginning, and they do not answer what nothing means in a rigorous sense. They show that the universe evolved from a hot, dense, simple state into a cooler, structured one. They show that rewinding is not imagination, but inference anchored in measurement. The mystery is real, yet it is fenced in by facts. So the first task here is mechanical, not mystical. We trace what expansion implies, step by step, until the steps become uncertain and the equations start to warn us. The mystery grows later, after the evidence has done its work. In this chapter, we keep our hands on the rail. Start with today's universe, where galaxies cluster along filaments and voids in a web that spans unimaginable distances. On screen, the cosmic web looks like frost spreading on glass, bright nodes, thin strands, and vast, dark cavities. The average density is low, and most of space is cold and dark, with matter concentrated into islands. The microwave background is only 2.7 Kelvin, a whisper of heat spread thin by expansion and almost perfectly uniform. Rewind to the era of the first stars, when the cosmic dark ages ended and the first steady lights switched on. Gravity pulled gas into the first halos, and the densest pockets collapsed until nuclear fusion ignited. Starlight began reionizing hydrogen, changing the transparency of intergalactic space and reshaping how later galaxies grew. This is already complex astrophysics, but it sits on top of a simpler expanding background that sets the overall density and cooling rate. Rewind further to recombination, about 380,000 years after the hot beginning-like state described by the model. Before this time, the universe was a plasma of electrons and nuclei, with charged particles roaming freely. Photons scattered constantly off free electrons, so the universe was opaque like a fog made of charge. Light did not travel far before it was redirected, and the cosmos behaved more like the interior of a star than empty space. As expansion cooled the plasma, electrons combined with nuclei to form neutral atoms, mostly hydrogen and helium. With fewer free charges, photons stopped scattering so often, and the mean free path of light grew dramatically. Light could then travel long distances, and that released the microwave background we measure today. In visual terms, the fog thinned until the first clear horizon appeared. Recombination is not the beginning of light, and it is not the first energy release in cosmic history. It is the moment the universe became transparent to most photons, which is a different and more specific claim. It is a visibility boundary, and it is why our direct electromagnetic view stops there. Beyond it, earlier photons exist in principle, but they were trapped in the plasma and could not stream freely to us. We wind earlier to Big Bang nucleosynthesis, within the first few minutes, when the universe was a furnace of nuclear reactions. Temperatures were high enough to fuse protons and neutrons into light nuclei, but not high enough to build heavy elements efficiently. The outcome depended on how quickly the universe expanded and cooled through key thresholds, especially the moment when deuterium could survive without being blasted apart. This brief window set the primordial helium fraction that later generations of stars inherited. At these times, the universe was still too hot for stable atoms, and electrons were not bound to nuclei. It was a nuclear environment, not a chemical one, and the familiar periodic table had not yet emerged. The story is simpler than later galaxy formation, because it is governed by well-tested particle and nuclear physics. In a sense, the early universe is easier to calculate than the later one, because it is more uniform. Rewind earlier still to the quark-gluon plasma, when protons and neutrons were not yet bound states and quarks moved more freely. Quarks and gluons formed a hot, dense soup, where confinement had not yet locked quarks into hadrons. Laboratory heavy ion collisions recreate hints of this phase, though the cosmic version was far larger and longer lived. The comparison is imperfect, yet it anchors the idea that early universe phases are not pure speculation. Continue rewinding and the labels become tentative, because we approach energies beyond direct experiment and beyond comfortable extrapolation. Electroweak symmetry restoration becomes relevant, and particle species behave differently as masses and interactions shift with temperature. The universe is still describable with known physics for a while, but the confidence gradually thins. At some point, we are leaning on theories that have not been tested in the required regime. At each stage, expansion is the organizing principle, because it sets the conditions that decide what can happen. Expansion sets the temperature and density, which set reaction rates and equilibrium conditions, and those rates decide what survives. When reaction rates fall behind the expansion rate, processes freeze out and leave relics behind. The universe does not choose to stop reacting. It simply becomes too dilute and too cool to keep up. Those relics are the reason the rewind is not just storytelling, even when we use metaphors to keep it intuitive. Element abundances are relics of nuclear freeze-out, preserved in ancient gas and measured in spectra. The microwave background is a relic of photon decoupling, carrying a snapshot of the plasma's last scattering. Large-scale structure is a relic of early fluctuations amplified by gravity, turning tiny differences into galaxies and voids. The phrase, "tracing the Big Bang backward," can still mislead if we forget what is being traced in the mathematics. We are not tracing objects back to a single point in space, as if we could reverse their trajectories like billiard balls. We are tracing the scale factor back to smaller values, where the whole universe was denser everywhere. The rewind is about conditions, not coordinates. This is also where the word beginning needs discipline, because it carries more baggage than the data do. The standard Big Bang model describes an early hot phase and its expansion with impressive success across many observations. If we extrapolate the equations too far, classical general relativity predicts a singularity, where density and curvature diverge. That divergence is a mathematical statement about the limits of the model, not a camera-ready event. A singularity is not a filmed moment, and it is not a physical object with a location you could point to. It is a sign that the theory has been pushed beyond its domain of validity, where new physics is expected to matter. It is like a warning label that says the map has ended, not that reality has ended. The cliff is in the equations, and we do not yet know what landscape lies beyond. The closer we rewind, the more we rely on assumptions that may fail in subtle ways. We assume space-time is smooth, and that general relativity remains valid at arbitrarily high curvature. We assume quantum fields live on that space-time in the usual way, with familiar notions of particles and vacuum. Near the earliest times, those assumptions may conflict, And the conflict is not merely philosophical. It is a technical problem about how to unify gravity with quantum mechanics.
This is where nothing often sneaks back into the conversation as a placeholder for ignorance, dressed up as certainty.
When the equations break, people imagine a blank before the first describable moment, like an empty stage before the curtain rises. But a breakdown in description is not evidence of emptiness, and it is not evidence of non-being. It is evidence that our tools are incomplete, which is a different and more honest claim.
What we can honestly say is narrower, and it is still profound when you sit with it. The universe was once in a state where matter, radiation, and geometry were tightly coupled, exchanging energy rapidly and evolving together. It expanded and cooled, leaving measurable relics that still fill the sky and still shape what can form. We live inside the afterglow of that coupling, even if we rarely notice it. Modern cosmology also refines the expansion story beyond Hubble's first relation, turning a straight line into a detailed history. We measure that expansion has changed rate over time, and we reconstruct that change using multiple cosmic probes. In the recent universe, expansion appears to be accelerating, attributed to dark energy or a cosmological constant-like component. The acceleration is inferred from how distant objects appear dimmer or brighter than expected, given their redshift. That late-time acceleration does not erase the early hot story, but it complicates the full rewind in important ways. It means the expansion history is not a single simple curve, and it changes how we translate redshift into distance and time. It also reminds us that what fills space affects how space expands, because energy density and pressure enter the gravitational dynamics. Space is not a passive arena. It responds. Even the phrase recession speed needs care because it can exceed the speed of light at great distances without any paradox. That does not violate relativity because it is not motion through space like a rocket crossing a track. It is the growth of space between regions, which relativity allows because the limit applies locally to objects moving through space-time. The distinction is technical, yet it prevents a common misunderstanding from hardening into a false objection. This distinction matters for the central question, because it changes what we imagine the Big Bang to be in the first place. If space itself is dynamic, then nothing cannot mean an empty container waiting for contents to arrive. The container is part of the phenomenon, and it has a measurable history written into the sky. In cosmology, geometry is not background scenery. It is an actor. The raisin bread picture also guards against a common mistake about everywhere at once, which can sound like a trick of language. It does not mean every place was once the same point, compressed into a single location. It means every region we can name was once much closer to every other region in a hotter, denser state. The early universe was small in scale, not localized in space. The evidence also forces a subtle shift in how we talk about origins, because it separates what we can observe from what we can only extrapolate. We can infer conditions back to recombination with direct photons, and we can test those in exquisite detail. We can infer earlier conditions with nuclear and particle physics, supported by relics and consistency checks. We cannot yet infer with equal confidence what happens at the boundary where quantum gravity matters, because we lack the needed theory and the needed data. This is the documentary's working posture, and it keeps the mystery honest rather than inflated. We treat the Big Bang as a well-supported description of early evolution with clear empirical anchors. We do not treat it as a complete account of ultimate origin or as proof of philosophical nothingness. The difference is not a retreat. It is a commitment to what the evidence actually says. Still, the rewind teaches a key lesson about simplicity, and it is a lesson with visual weight. Earlier times were not only hotter and denser, they were also more uniform, with fewer structures and fewer distinct environments. Many later complexities, like stars and chemistry, did not yet exist because the universe had not cooled enough for them. The early cosmos is not empty, but it is smooth, like a nearly unwrinkled fabric. Uniform does not mean featureless, and the microwave background proves that with its faint mottling across the sky. Tiny variations were present,
And they mattered, because gravity can work with very little given enough time. They were small enough to keep the early universe smooth, and large enough to seed everything that followed.
A difference of 1 part in 100,000 becomes a galaxy if you wait long enough.
The early universe was also a place where equilibrium often held, because interactions were fast and energies were high. Particles were created and destroyed in pairs, and energy moved freely among species, keeping distributions close to thermal forms. As expansion continued, equilibrium broke in stages, leaving fossil imprints in abundances and backgrounds.
Each freeze-out is like a snapshot taken when the shutter speed finally beats the motion.
These stages give us a calm scaffold for time, even when the numbers feel abstract and the scales resist intuition. Minutes for nucleosynthesis when the first nuclei formed and the chemical baseline was set. Hundreds of thousands of years for recombination, when the fog lifted and light finally traveled freely.
Hundreds of millions of years for the first stars, and billions for the cosmic web we inhabit, with its filaments and voids.
When we say the universe had a beginning-like state, we mean something specific rather than poetic. We mean there is a finite past to the hot, dense phase described by our best-tested equations, and that phase leaves measurable relics. We also mean that pushing beyond that phase requires new physics, not just better telescopes or larger surveys.
The limit is not simply distance, it is theory.
This is where the central question returns with sharper edges, because the rewind brings us to a boundary that feels like an origin. If our map ends at a boundary, is that boundary a true beginning in any physical sense? Or is it a transition point, where time and space as we know them emerge from something deeper? If the equations are silent, what would it even mean for before to exist?
The expansion evidence does not decide between those options by itself, and it never claimed it could.
It tells us the universe evolved from hot and dense to cool and structured, and it tells us how that evolution proceeds. It tells us the early universe was once opaque, and then became transparent, leaving behind a background of ancient light. It gives us a narrative with a horizon, and it dares us to ask what lies beyond it.
Now the narrative tightens around that transparency boundary,
because it is our clearest observational horizon and our most detailed data set. The microwave background is not just a glow, it is a timestamp, stamped across the entire sky with remarkable uniformity. It is the earliest surface from which light can reach us directly, and it arrives from all directions with the same ancient origin. When we map it, we are mapping a moment in time, not a place in space.
If the universe was once an opaque plasma,
then there was a first time light traveled freely over cosmic distances. That first free streaming light is still here, stretched into microwaves by expansion, and cooled into a near-perfect black body. It carries a coded message about the conditions that made the universe transparent, including the density of ordinary matter and the geometry of space. The code is subtle, written in tiny anisotropies and polarization patterns.
Next, we follow that first light in detail, because it is both a limit and a guide.
We ask what the microwave background reveals about the young universe's composition and geometry, and why its patterns are so mathematically informative. We also ask what it cannot reveal, and why that gap is where nothing becomes tempting again. When the oldest light stops, imagination tries to fill the darkness.
We end this chapter with a boundary, not a conclusion,
because boundaries are where science becomes most honest. The rewind brings us to a sky filled with relic radiation, and then to a fog we cannot see through. The next step is to understand exactly what happened when the fog lifted, and what the released light still tells us now. The universe has given us a first page we can read, yet it has not handed us the cover. We have rewound the universe to a hard observational edge, where the sky becomes a historical record written in light. The cosmic microwave background is that record, and it is the oldest light we can see with electromagnetic eyes. It answers many questions about our origin story, while sharpening the central question about nothing and before. Visually, it is tempting to imagine a spotlight aimed at the beginning, as if the cosmos has a single stage. The CMB is not that kind of beacon, and it is not a glow from a single place. It is radiation arriving from every direction, an all-sky afterimage, released when the universe first became transparent. When we measure it, we are measuring a time, not a location, because the light left everywhere at once. In the earliest eras, the universe was a hot plasma, a seething mixture of electrons, protons, helium nuclei, and photons.
Temperatures were high enough that atoms could not hold together because collisions and energetic photons tore them apart. Charges were free, so light could not travel far without scattering off electrons through Thomson scattering, a process that is simple in principle and relentless in practice. Photons bounced constantly, and the universe behaved like a dense fog made of charged particles, bright yet visually blind.
Imagine trying to see through a cloud that is luminous from within, where every step of a photon is interrupted. In that fog, seeing earlier with ordinary light was impossible, because the light never streamed freely in straight lines. Each scattering erased directional information, scrambling what would otherwise become an image. The early universe could glow intensely and still hide its own past, because opacity is not darkness, it is confusion. As expansion continued, the plasma cooled, and the balance of reactions shifted in a way that cosmology can calculate precisely. The key change was not merely that the universe got colder, but that it crossed a threshold where stable neutral atoms could persist. Protons and electrons could finally bind into neutral hydrogen, with helium forming neutral atoms too, although helium recombined in stages. This process is called recombination, though it was the first stable combination in cosmic history, and the name is a historical artifact. The physics is subtle, because recombination is not a single instant and not a perfect switch. Even as neutral hydrogen forms, a small fraction of electrons remain free, and that residual ionization still matters for scattering. Yet the trend is decisive. With fewer free electrons, photons stop scattering so often, and their mean free path grows enormously. The universe goes from a place where a photon travels centimeters before being redirected, to a place where it can travel for billions of years. That moment is also called photon decoupling, because radiation stopped being tightly coupled to matter. Before decoupling, photons and baryons behaved like a single fluid, exchanging momentum so frequently that they moved together. After decoupling, the photons began to free stream, while matter was left behind to respond mainly to gravity. The universe transitioned from opaque to transparent over a relatively short cosmic interval. And that shortness is part of why the CMB is such a clean snapshot. The released photons began free travel, and they have been traveling ever since, crossing expanding space like messages in a stretching bottle. Their wavelength stretched with the expanding universe, cooling their temperature as the scale factor grew. What began as visible and infrared light in a hot young cosmos is now microwave radiation in a cold, mature one. Expansion does not merely move galaxies apart. It dilutes and reddens the radiation field, turning heat into a faint whisper. The CMB we detect today is those same photons, redshifted into microwaves by cosmic expansion. Its spectrum is an almost perfect blackbody, which is a strong clue about its origin, and an even stronger constraint on alternatives. A blackbody curve implies the early radiation field was in near thermal equilibrium with matter, meaning energy was exchanged efficiently enough to erase spectral features. The best fit temperature today is about 2.725 Kelvin, a precise number that acts like a cosmic thermometer and a calibration standard. This precision has a history, and that history matters because it shows how evidence hardens into knowledge. In the 1940s, theorists such as George Gamow, Ralph Alpher, and Robert Herman argued that a hot early universe should leave behind a cooled relic radiation field. In 1965, Arno Penzias and Robert Wilson found an unexplained microwave hiss that came from every direction, and the interpretation quickly followed. The discovery did not merely add a new observation. It transformed cosmology into a measurement science because the sky itself became a laboratory. The timing matters because it anchors our timeline with a clear observational timestamp. Recombination happened about 380,000 years after the Big Bang hot phase began, when the temperature dropped to roughly 3,000 Kelvin. That is early compared to galaxies, but late compared to nucleosynthesis and earlier particle physics eras. It is the earliest surface from which electromagnetic signals can reach us directly, a kind of last scattering shell surrounding our viewpoint. This is why the CMB is both a window and a wall. It is a window because it carries detailed information about the young universe's contents and geometry, encoded in subtle patterns across the sky. It is a wall because earlier photons were trapped, repeatedly scattered, and unable to preserve a straight path to us. To go earlier than this with light, we would need a different messenger than photons, or a different kind of inference. The CMB looks smooth at first glance, like a nearly uniform bath of microwaves. Yet it is not perfectly uniform, and the deviations are the most valuable part of the signal. It contains tiny temperature anisotropies across the sky at the level of about 1 part in 100,000. That is roughly 10 to the minus 5, a pattern of microkelvin scale ripples on top of the 2.725 K average. And those ripples are not measurement noise. On a full sky map, those fluctuations appear as mottled patches, warm and cool spots spread across a sphere. The colors are false, but the information is real, and the contrast is dramatically exaggerated for human eyes. Beneath the artifice of the palette is a statistical structure that can be tested, compared, and refined. The universe is not painting randomly. It is leaving fingerprints of physics. These anisotropies are the imprint of small variations in density, velocity, and gravitational potential in the early plasma. Where the plasma was slightly denser, gravity pulled inward more strongly, deepening potential wells. Where it was slightly hotter or moving differently, pressure and motion changed the local photon distribution, shifting the observed temperature. The CMB encodes these conditions as a snapshot of the universe at last scattering, with multiple physical effects layered together. Some of those effects are intuitive once named, even if the details are technical. Photons climbing out of gravitational wells lose energy, which shows up as cooler spots, while photons falling into wells gain energy on the way in. Motion matters too, because a patch of plasma moving toward us slightly blue shifts its photons, and moving away slightly red shifts them. Even the thickness of the last scattering surface matters, because recombination took time, and that time blurs the finest details. To read that snapshot, cosmologists translate the sky map into statistics, because the sky is one realization of a probabilistic early state. They compute the angular power spectrum, which measures how much variation exists at different angular scales. The result is not random, because it shows a series of peaks and troughs that repeat with a regularity. Those features are called acoustic peaks, and they are central to modern precision cosmology. The phrase acoustic is literal in a physical sense, even though the medium was not air and no ears could hear it. Before recombination, the plasma supported sound waves, which were pressure waves in a coupled photon-baryon fluid. Gravity tried to compress overdense regions, and radiation pressure pushed back with the stiffness of light itself. The competition drove oscillations, and the CMB froze those oscillations at the moment photons decoupled, like a chord stopped mid-vibration. It helps to picture the early universe as a vast, resonant medium, where small perturbations ring like ripples in a cosmic ocean. Overdense regions begin to collapse, but the trapped photons resist compression, pushing outward and creating rarefactions. The oscillations have phases, compression and expansion, and recombination captures those phases at different scales. What we see as peaks is the statistical memory of that ringing. The first peak corresponds to a characteristic scale, the sound horizon at recombination. It represents the largest distance a sound wave could have traveled in the plasma before decoupling, given the finite time and the speed of sound in that photon-baryon mixture.
Subsequent peaks reflect harmonics, like a resonant instrument with multiple modes, each mode representing a different oscillation phase. Their positions and heights depend on the universe's composition and expansion history, which is why the spectrum becomes a parameter measuring machine. Ordinary matter affects the peaks in a specific way that is both subtle and decisive. Baryons add inertia to the oscillating fluid, enhancing compressions relative to rarefactions, because heavier matter falls more deeply into gravitational wells before pressure can reverse it. That shifts the relative heights of odd and even peaks, leaving a measurable signature. From this, the CMB tells us how much normal matter exists, even when much of it is dark gas between galaxies and not shining. Dark matter enters the story because baryons alone cannot explain the observed pattern and later structure growth. Dark matter does not couple to photons, so it does not participate in the pressure-driven oscillations in the same way. It provides gravitational wells that begin forming earlier, even while baryons are still tied to radiation and prevented from collapsing efficiently. The CMB peak structure strongly supports a large dark matter component in the cosmic budget, because the data require gravitational scaffolding without extra radiation pressure. The CMB also constrains the geometry of space on the largest scales we can test. The angular size of the sound horizon depends on how light rays travel through expanding space-time, which in turn depends on spatial curvature. Measurements show the universe is very close to spatially flat, within tight uncertainties that have narrowed over decades of observations. Flatness here is a statement about large-scale curvature, not a claim about infinite extent, and it is one of the most striking empirical results in cosmology. The CMB's black body spectrum is another crucial piece of evidence, because it is unusually clean in a universe full of messy astrophysics. Many processes produce spectra with lines, bumps, and distortions because atoms and dust leave fingerprints at specific wavelengths. A near-perfect blackbody is what you expect from a hot, dense, early universe that was once in equilibrium, where repeated interactions smooth everything into a thermal curve. It is hard to reproduce that spectrum with later starlight and dust alone, because later sources tend to add features rather than erase them. This is where the CMB becomes a time machine with a calibration label, not merely a poetic metaphor. We do not guess its age from storytelling, because its properties match a consistent thermal history that can be checked against multiple datasets. Expansion cools radiation in a predictable way, and the CMB temperature fits that scaling with remarkable accuracy. The same framework also fits nucleosynthesis and the growth of structure, linking chemistry, gravity, and radiation into one timeline. Yet the CMB is not only temperature, and it is not only a static picture. Polarization patterns add another layer, produced by scattering in the presence of local quadrupole anisotropy, which is a technical way of saying the radiation field had a directional pattern. Polarization is faint, but it is rich, because it separates different physical contributions that temperature alone can mix together. It also carries information about later reionization, when the first stars and galaxies reionized hydrogen and caused additional scattering. When polarization is mapped, it forms swirling and gradient-like patterns that can be decomposed into E modes and B modes. E modes are expected from density perturbations and have been measured robustly, reinforcing the same cosmological story told by temperature. B modes are more elusive, because they can be generated by gravitational lensing, and in some models, by primordial gravitational waves. The promise is profound, but the measurement is difficult, and the signals sit near the edge of what instruments can reliably separate from foregrounds. From this single dataset, cosmologists infer a compact set of parameters that describe the universe well, almost like reading an ID card of the cosmos. The standard model is called lambda CDM, shorthand for a cosmological constant like dark energy plus cold dark matter. It also includes ordinary matter, radiation, and an initial spectrum of primordial fluctuations, often summarized by an amplitude and a spectral tilt.
Lambda CDM is not a metaphysical claim, but a best-fit description that matches CMB and large-scale structure with impressive economy.
The success is partly methodological, because CMB experiments are designed to isolate a primordial signal from a noisy sky. Our galaxy emits microwaves through synchrotron radiation and dust, and those foregrounds must be modeled and subtracted carefully. Instruments scan the sky repeatedly, building sensitivity through redundancy, and calibration is tested against known sources and internal consistency checks. The result is a map that is both a triumph of engineering and a triumph of statistical discipline. Dark energy enters gently because it is not dominant at recombination, yet it shapes the universe's later expansion in a way that feeds back into what we infer. The CMB constrains dark energy indirectly through geometry and distance relationships, because the path from recombination to us depends on the expansion rate over cosmic time. Combined with galaxy surveys and supernova measurements, the fit points toward late-time acceleration, an expansion that speeds up rather than slows down. The name dark energy marks our ignorance about its physical nature, not a settled mechanism. The CMB also connects directly to how galaxies formed, which returns us to the question of seeds and growth. The anisotropies represent small initial density fluctuations, and they are small enough to be treated statistically and, to first approximation, linearly. After recombination, baryons are no longer locked to photons, so they can fall into gravitational potential wells without being held up by radiation pressure. Over billions of years, gravity amplifies small contrasts into large structures, turning a nearly uniform universe into a web. The growth is not uniform because gravity is non-linear once overdensities become significant and feedback processes begin to matter. Regions slightly denser than average attract more matter, becoming denser still, and the process accelerates as mass accumulates. Regions slightly underdense lose matter to their surroundings, becoming voids that expand and empty out. This process builds the cosmic web, with clusters at nodes and filaments connecting them, while vast dark spaces open between the luminous islands. If we could fly through a simulation that starts from CMB-like initial conditions, we would watch faint ripples sharpen into structure. Filaments would emerge first as subtle threads, then thicken as matter streams along them under gravity's pull. At the intersections, halos would deepen, gas would shock and cool, and galaxies would ignite as stars begin to form. The visual drama is immense, yet the cause traces back to fluctuations that were only tens of microkelvin. Dark matter is crucial in this growth story because it begins clustering earlier and more efficiently, unconstrained by photon pressure. While baryons were pressure-supported by radiation, dark matter could already form halos, creating potential wells that persist through recombination. After recombination, ordinary matter falls into those halos and cools, eventually forming stars and galaxies through complex astrophysics. The CMB's small ripples therefore become the blueprint for later cosmic architecture, a plan drawn in temperature and executed in gravity. This is the remarkable compression of the CMB narrative, and it is worth lingering on the scale of that compression. A map of microkelvin variations becomes an explanation for galaxies, clusters, and the large-scale web, spanning a factor of 1,000 in cosmic time. The universe's largest structures trace back to fluctuations that were tiny and nearly Gaussian, meaning their statistics resemble a simple random field with small deviations. The sky's faint mottling becomes a fossil record of initial conditions, preserved with extraordinary fidelity. Precision makes the story sharper, but it also creates tension that the documentary cannot ignore. The CMB is so informative that it tempts us to think we have reached the beginning, because the data feel foundational. Yet it is also a boundary that blocks direct electromagnetic access to earlier times, no matter how large we build our telescopes. The better we measure the wall, the more we feel the absence of what lies beyond it, and the more the word origin starts to wobble. This is where the central question returns with a new angle, almost like a refrain in a darker key.
If we rewind past every galaxy and past every atom, we still do not reach philosophical nothing. We reach a plasma that hides its earlier history behind scattering, a physical barrier rather than a metaphysical one.
The CMB is the first light we can see, not the first event that happened. And that distinction carries weight. The wall forces a methodological shift, and the documentary must name it clearly. Before recombination, the universe is not invisible because it did not exist, and it is not invisible because it lacked light. It is invisible because photons could not carry a clean image across it, since scattering erased the memory of direction. The limit is not only distance, but the physics of opacity, and opacity is a property of matter and radiation together. Other messengers might cross that earlier era more freely, at least in principle, and the idea has a long pedigree in cosmological thinking. Neutrinos decouple earlier than photons because they interact weakly, and gravitational waves could travel with minimal scattering, because space-time ripples barely notice matter. Those relic backgrounds are harder to detect, and for now they remain mostly theoretical targets that test the limits of instrumentation. The CMB remains our most detailed and reliable early snapshot, because it is both bright enough and clean enough to measure. Even within the CMB, there are hints that point toward earlier processes, like footprints leading away from the visible boundary. The pattern of fluctuations is consistent with a nearly scale-invariant spectrum of primordial perturbations, meaning similar power across a wide range of scales with a slight tilt. That kind of spectrum is naturally produced by inflationary models, where quantum fluctuations are stretched to cosmic scales by rapid expansion. The CMB does not prove inflation by itself, but it strongly motivates it as an explanation, because alternative mechanisms struggle to match the same simplicity. It is worth pausing on what that claim really means, in plain language. Quantum fields fluctuate even in their lowest energy states, producing temporary variations that normally remain microscopic. Inflation, if it happened, would take those tiny variations and expand them to astronomical sizes, turning quantum noise into the seeds of galaxies. The CMB then becomes a bridge between quantum theory and the largest structures in nature, a connection that feels almost impossible until the data insist on it. Inflation, if it occurred, would push our narrative closer to the question of nothing, but it does so in a way that complicates the word. It often invokes a high-energy vacuum-like state that drives accelerated expansion, and that state can behave like a repulsive gravity in general relativity. That state is not empty in the philosophical sense, because it has fields, energy and dynamics, and it can decay into particles and radiation. Still, it shifts the origin story from a hot beginning to a transition from one physical state to another, and transitions invite deeper questions. Precision also reveals stress points that keep the mystery alive, even as the model succeeds. Measurements of the Hubble constant show tension between early universe inference from the CMB and late universe distance ladders, and the discrepancy has persisted through improved datasets. The difference may be systematic, or it may hint at new physics beyond lambda CDM, such as additional components or subtle changes in early expansion. Either way, it reminds us that the model is powerful, not final, and that the universe can still surprise us. There are also conceptual limits that no improvement in microwave telescopes can remove, because they are built into the nature of the signal. The CMB is a snapshot of a surface, not a movie of earlier times, and a surface contains only so much information about what preceded it. It tells us conditions at last scattering, then relies on theory to connect those conditions to earlier epochs, through equations we believe we understand. As we push earlier, we lean more heavily on extrapolation, and the meaning of tested becomes more fragile. So the CMB becomes a paradoxical guide, both generous and withholding. It gives us a precise inventory of the universe at 380,000 years, including matter content and curvature constraints, and it does so with a confidence that is rare in deep-time science. It also tells us that earlier times are hidden behind an opacity barrier that no optical trick can bypass. The more clearly we see the first light, the more clearly we see what we cannot see,
and that clarity has its own kind of suspense. This is where the language of before starts to strain again, even in a data-driven chapter that is anchored in measurement. The CMB does not show a moment of creation, and it does not show a boundary of non-being, because it is not that kind of evidence. It shows a transition in transparency, which is a physical change inside an already existing space-time history, governed by atomic physics and expansion. If time itself emerged earlier, the CMB cannot directly display that emergence because it is already downstream of it. The documentary's tone shifts here from explanation to suspense, without leaving the evidence behind. We can read the universe back to recombination with photons, and we can test that reading with independent measurements and internal consistency. We can infer earlier epochs with particle physics and consistency checks, using the CMB as a boundary condition. But at some point, the chain of inference approaches an era where quantum gravity may matter, and our tested equations may fail, not from laziness, but from principle. The CMB therefore sits at the midpoint of our journey toward nothing, and it earns that central place through both physics and symbolism. It is the oldest light, and it is the cleanest relic of the early hot universe that we can map in detail. It is also a wall that forces us to ask what counts as an origin, and what counts as an explanation, when evidence has a horizon. It turns the sky into a time machine, then stops the machine at a locked door, leaving us with the sound of our own questions. To go earlier than the CMB, we must rely on theory, and theory must be disciplined by what the CMB already fixes. We will carry forward the parameters that the first light has pinned down, including the matter budget and the shape of primordial fluctuations. We will also carry forward the humility that comes with an observational horizon, because horizons are not just distances, they are limits on information. Beyond the wall, equations begin to hint at a singularity, and the word nothing waits in the gaps. Next, we step past the first light using models that reach into the opaque era, where the universe is still bright, but not yet transparent. We follow inflation, quantum fluctuations, and the limits of general relativity as we rewind further, guided by the patterns frozen into the microwave sky. We approach the edge where space-time itself may become uncertain, and where before may stop behaving like time. The first light fades behind us, and the darkness ahead is not empty. It is unknown. We have followed the evidence back to the first light, and the trail keeps narrowing as the universe grows stranger. Past recombination, we rely on equations more than photons, and the central question sharpens into a philosophical-sounding problem with technical teeth. What, if anything, could have existed before the Big Bang? And what does nothing mean when time itself is in question? Rewinding the universe is not only a story about hotter matter and brighter radiation. It is also a story about geometry becoming extreme, until the math stops behaving in ways we can physically interpret. General relativity is our best tested theory of gravity, and it treats gravity as space-time curvature rather than a force in the usual sense. Matter and energy tell space-time how to curve, and curved space-time tells matter how to move. Visually, that relationship is often drawn as a grid that bends under a weight, yet the real picture is four-dimensional and dynamic. The bending is not just spatial because time participates in the geometry and responds to energy as well. Clocks tick at different rates in different gravitational potentials, and rulers measure different distances when space itself stretches. In the expanding universe, the grid is not merely warped, it is evolving everywhere at once. The same equations that predict Mercury's perihelion shift also describe how the entire cosmos changes with time. In cosmology, that relationship becomes a set of expansion equations tied to density and pressure. They are the Friedmann equations, derived from Einstein's field equations under the assumption that the universe is homogeneous and isotropic on large scales. That assumption is not perfect, yet it is extraordinarily effective once we average over galaxies and voids. It turns the universe into a kind of cosmic fluid, with a scale factor that measures how distances between co-moving points grow.
In that fluid picture, pressure matters because it gravitates. Relativity counts it as part of the source.
As we rewind, the scale factor shrinks and the energy density rises, and the temperature climbs in lockstep. Radiation grows more important than matter because radiation energy density scales more steeply with compression. Photons are diluted by expansion, but their wavelengths are stretched too, so their energy changes with the scale factor.
Curvature terms grow, and the gravitational field strengthens in a precise mathematical sense.
The same framework that explains gravitational lensing and black holes is the framework we push toward time zero. A useful visual is a simple plot where the scale factor slides downward toward a boundary, while density and curvature shoot upward like a needle. At first, the curves rise gently, then they steepen, and then they appear to go vertical.
The graph feels like a warning, because it suggests not merely large numbers, but a breakdown in the language of the model.
We are not just rewinding a movie, we are testing whether the film itself can exist. But the rewind has a cliff edge, and the name of that edge is singularity. In general relativity, a singularity is where certain quantities diverge, like density and curvature.
The equations keep running, yet their outputs become infinite or undefined, which is rarely a sign of a literal infinity in nature. A model that predicts infinities is often telling us it has left its domain. In practice, physicists look to coordinate-independent measures, like curvature invariance, to see whether the blow-up is real or just a bad choice of coordinates. This is the first misconception to disarm, because the word singularity sounds like an object. It is easy to picture a tiny point, a physical dot where the universe began, like a seed that suddenly exploded.
In the math, a singularity is not necessarily a real place you could visit with coordinates and instruments. It can be a sign that the coordinates, assumptions, or the theory itself have been pushed too far. Even in familiar black hole metrics, some apparent singularities vanish when you change coordinates, which is a cautionary lesson.
The key idea is breakdown, not discovery, and that distinction changes the emotional tone of the origin story.
Classical general relativity assumes space-time is smooth at all scales, like a differentiable fabric that can be curved at a point with unlimited precision. It assumes we can define curvature locally using calculus, even when we zoom in without limit. It assumes the gravitational field can be treated classically, even when energies become enormous.
Those assumptions are not metaphysical claims. They are working rules that have earned trust in every regime we can test. Those assumptions work brilliantly in ordinary regimes, and they may fail near the beginning. We have tested relativity in the solar system, in binary pulsars, and now in gravitational waves from merging black holes. Yet all those tests occur where space-time curvature, while dramatic, is still far from the most extreme values the equations allow. The early universe asks the theory to operate in a regime we have never directly probed. It is the difference between testing a bridge in a storm and asking it to survive the pressure at the bottom of an ocean. A singularity is therefore a warning that our extrapolation has become untrustworthy. It is like a map that ends with a blank margin and a note that says, "Here be dragons," except the dragons are mathematical pathologies. The blank margin is not proof that nothing exists beyond it. It is proof that the cartography has run out. In science, that moment is oddly productive because it tells us exactly where new principles must enter. In the Big Bang context, the singularity appears when we run the Friedman solutions backward. Density rises without bound as the scale factor approaches zero, and the temperature climbs toward values where particles and forces behave in unfamiliar, unified ways. Curvature invariance can blow up, signaling that space-time becomes infinitely curved in the model. The proper time along many paths cannot be extended further into the past, as if history hits a boundary. The boundary is not drawn on a calendar, but in the mathematical structure that defines what earlier even means. That last phrase matters because singularities in relativity are not defined as infinite density points first. In modern relativity, the deeper definition is geodesic incompleteness,
which sounds abstract but is physically sharp. A geodesic is the path a free-falling observer follows through space-time, the closest thing relativity has to straight lines. If the space-time cannot be extended so that such paths continue smoothly, the space-time is incomplete. In other words, the theory cannot supply a continuous history for ideal observers, even before we talk about what matter is doing.
Imagine an astronaut falling freely, carrying an ideal clock, tracing a path backward toward the beginning. In an incomplete space-time, the clock's reading reaches a finite value, and then the mathematical description simply stops. There is no earlier tick within the same classical geometry. Not because the astronaut hits a wall in space, but because the concept of the path fails. The boundary is in the structure of space-time itself. Visually, the world line ends like a pencil stroke that reaches the edge of the page. This is where the Hawking-Penrose singularity theorems enter, at a high level, and they arrive with historical weight. In the 1960s and early 1970s, as relativists argued about whether singularities were artifacts of symmetry, these theorems showed they were far more robust. They do not rely on the universe being perfectly smooth, and they do not require special coordinates. They show that under reasonable physical conditions, classical general relativity predicts incompleteness. Historically, this was a turning point, because it reframed singularities from curiosities into generic features of the classical theory. The conditions include things like positive energy density and the presence of trapped surfaces or cosmic expansion. In simple terms, they assume gravity is attractive in the way ordinary matter makes it attractive, and they assume space-time obeys certain causal rules. The conclusion is not that a point of infinite density must literally exist in nature. The conclusion is that classical space-time cannot be extended indefinitely into the past. It is a theorem about the limits of the classical description, not a certificate of an actual infinity. That is a subtle but crucial shift in meaning, and it is easy to miss in popular retellings. The theorems do not tell us what replaces the boundary, and they do not provide a photograph of an origin event. They tell us that something must replace the classical description, because the classical description cannot be complete. The central question becomes less about a first object and more about a limit of space-time itself. When the math says incomplete, it is quietly asking for a deeper layer of physics. If we take the theorem seriously, the Big Bang singularity is not a photographed event. It is a statement that our classical model predicts its own failure when pushed far enough, which is a very different kind of claim. That failure might correspond to a true beginning, or to a transition, or to a bounce. The theorems do not decide between those options because they do not include quantum gravity. They are like a sign that reads, "Bridge ends," without telling you whether there is a tunnel, a ferry, or another continent beyond. To understand why quantum gravity matters, we need a scale where our familiar categories stop working. That scale is set by the Planck units, built from the speed of light, Planck's constant, and Newton's constant. They are not arbitrary, and they mark where quantum effects of gravity are expected to become important. They are the unique scales you can form when you demand that relativity, quantum mechanics, and gravity all appear in the same expression. Historically, Max Planck introduced these combinations in 1899, long before anyone knew they would haunt cosmology. The Planck length is about 1.62 times 10 to the minus 35 meters, unimaginably smaller than an atom, and smaller even than the scales we associate with quarks. The Planck time is about 5.39 times 10 to the minus 44 seconds, unimaginably shorter than any laboratory timescale, and far shorter than the time light takes to cross a proton. These numbers do not prove that physics changes exactly there. They tell us that our current separation of theories becomes inconsistent there. If you pack enough energy into such tiny scales, the gravitational back reaction can no longer be ignored. A vivid way to picture it is to imagine zooming in on space-time like a camera diving into a landscape. At ordinary scales, the terrain looks smooth and the equations behave like reliable engineering. As the zoom deepens, the terrain becomes rougher, and the idea of a single, well-defined distance begins to wobble.
Near the Planck length, the camera reaches a regime where the very notion of resolution may be physically meaningless. The image itself seems to shimmer, as if the pixels were made of probability rather than points. In ordinary conditions, we treat gravity as classical and everything else as quantum. We quantize fields on a smooth background spacetime, and we compute particle processes using well-tested rules. That approach works because spacetime curvature is weak at the scales where quantum processes matter, at least in every experiment we can currently perform. Near the Planck scale, curvature itself becomes violent on quantum scales, and the background cannot be treated as fixed. The approximation of a passive stage breaks because the stage responds to the actors with comparable intensity. A useful way to say it is that the stage becomes part of the actors. Quantum uncertainty applies not only to particles and fields, but potentially to geometry, which is the stage on which physics plays out. If space-time fluctuates, then distances and durations are no longer sharp classical numbers. The very idea of a smooth manifold may be an approximation that breaks down. Even the notion of a single causal order, what can influence what, may become harder to define in the usual way. This is not merely poetic language, because quantum theory has a precise rule for uncertainty. If you try to confine energy to a very small region, quantum mechanics tells you the energy fluctuations become large. General relativity then tells you that large energy density curves space-time strongly, potentially creating horizons. Push that logic hard enough and the attempt to measure tiny distances could create gravitational effects that erase the measurement, an operational hint that classical space-time cannot be fundamental. The universe seems to protect its smallest scales, not with a wall, but with self-interference between our theories. So when we rewind to times earlier than about a Planck time, our equations are not just hard. They are conceptually mismatched, because we are combining incompatible frameworks that were never designed to coexist without modification. General relativity is deterministic and geometric, and quantum theory is probabilistic and operator-based. We do not yet have a complete theory that merges them in the regimes where both must matter. That absence is not a minor gap in a textbook. It is a missing foundation under the earliest chapter. This is where nothing can become an artifact of extrapolation. If we insist on pushing classical relativity all the way to a singular boundary, we manufacture a moment where time ends. Then we ask what came before that end, and we call the answer nothing. But that nothing may only mean our classical time coordinate stopped being meaningful. The word becomes a label for a failure of description, not a measurement of reality. The language of before is the next misconception to confront directly, because it sneaks in unnoticed. In everyday life, before means earlier on a universal clock, the same for everyone, everywhere. In relativity, time is not a universal background, and in cosmology it is tied to the geometry of the universe. Time is part of the system, not an external parameter that exists independently. When we ask for before, we may be asking for an extension of a coordinate that the theory itself refuses to extend. If time is part of the universe's geometry, then asking before time began may be a category error. The standard analogy is north of the North Pole, which is not a location you have failed to find. North is defined on the Earth's surface, and the North Pole is a boundary of that coordinate direction. Asking for a location north of it is not an unanswered question. It is a question that misuses the coordinate. The analogy is imperfect, but it signals a real logical trap. Some questions assume the very structure they are trying to probe. The analogy is imperfect, but it captures the logical structure, and it also hints at how physics sometimes resolves paradoxes. If the Big Bang marks a boundary to classical time, then before may not be a direction that exists in the classical description. The question may not be what was there earlier, but what replaces the concept of earlier. That is a different kind of mystery, and it is closer to the heart of the documentary. It also forces a humbling thought. Our intuition is tuned to clocks inside the universe, not to the universe as a whole. Still, we should not hide behind analogies because physics demands sharper statements. Cosmological time in the Standard Model is defined by the motion of the cosmic fluid, the average rest frame of matter and radiation. It is a parameter that works because the universe is homogeneous and isotropic on large scales. So there is a natural notion of co-moving observers. Near a singular boundary, that smoothness assumption may fail, and the definition of cosmic time may fail with it. If the fluid picture breaks, then the clock we use to label the rewind may no longer exist. Even the idea of a cosmic fluid is a controlled approximation, and it has a history. It emerged from the insight that on the larger scales, galaxies behave like molecules in a gas, and the details average out. That insight was strengthened by the discovery of the cosmic microwave background, which revealed an astonishing uniformity. Yet as we approach the earliest moments, the approximation becomes more fragile, because quantum fluctuations and extreme energies can dominate the dynamics. The smooth average that works for billions of light years may be meaningless at the smallest fractions of a second. So the before problem has two layers. One layer is semantic, because we import everyday time into a regime where it may not apply. The other layer is physical, because the equations that define time evolution may stop being valid. When both layers fail together, nothing becomes an easy placeholder. The honest move is to ask which part failed first: our language, our equations, or the underlying assumptions that connect them. A singularity, then, is not a claim that the universe emerged from literal non-being. It is a claim that our classical description cannot be extended, even if reality continues in some form. The gap between cannot be extended and nothing existed is where popular accounts often jump too quickly. The documentary has to keep that gap visible. That gap is where scientific humility lives, and where the next breakthrough would have to land. We can make the point concrete by comparing with other singularities we already know. In black hole solutions, classical relativity predicts a singularity inside the event horizon, and it predicts that tidal forces can grow without bound. Many physicists expect that quantum gravity will modify that interior, even if we cannot yet compute it. We do not treat the singularity as a confirmed physical object. We treat it as a sign that the classical solution is incomplete. The interior is hidden from external view, yet the mathematical warning is still loud. The same logic applies to the Big Bang singularity, even though it is not hidden behind a horizon in the same way. The Big Bang is a global feature of the cosmological solution, not a localized object in space. It is a boundary in time for the classical model, not a point in space where matter exploded. That distinction matters for how we imagine nothing. If everything is expanding away from everything else, there is no central location where the beginning happened. If the Big Bang is not an explosion into pre-existing space, then nothing before cannot mean an empty room waiting to be filled. The room is part of what is being described, and the room itself changes as the scale factor evolves. If the room's geometry becomes undefined, then the absence is not emptiness. The absence is a missing concept. The unsettling possibility is that our mental picture fails not because it is too small, but because it is the wrong kind of picture. This is where the Hawking-Penrose result becomes a narrative hinge, because it formalizes the idea of a boundary without overclaiming what lies beyond. Classical relativity, under broad conditions, predicts past incompleteness for expanding universes like ours. That suggests a boundary to classical space-time, not necessarily a boundary to reality. The theorems are powerful because they do not depend on the details of the matter content. They depend on general features like energy conditions and causal structure. In that sense, they are like a stress test for the very concept of classical space-time. But those energy conditions are themselves classical assumptions, and quantum fields can violate them in controlled ways. Quantum effects can produce negative energy densities locally, and vacuum states can have unusual stress-energy properties. Inflationary models, for example, involve an effective energy density that drives accelerated expansion, and that can behave unlike ordinary matter. That means the assumptions of the theorems may not hold in the earliest regime.
The theorems still matter because they tell us exactly which assumptions must be questioned. So the theorems do not close the door on before. They close the door on a purely classical before that obeys certain conditions, which is an important limitation. They tell us that if we want to go earlier, we need new physics. They also tell us that the central question is not only metaphysical. It is a technical question about what replaces classical space-time. The mystery is not just what happened, but what happened can mean when time is part of the system. At this point, the documentary's tone shifts from rewind to limit. We are no longer just tracing a timeline of phases like plasma to atoms to stars, as if the early universe was simply a hotter version of today. We are tracing the domain of validity of our theories, and watching that domain shrink as we approach the edge. The closer we get to time zero, the more the story becomes about the tools we use. The visuals can become more abstract here, equations floating over a fading grid, with the lines themselves beginning to fray. That does not mean the story becomes subjective, because the breakdown is not a matter of taste. The failure is encoded in the mathematics and in the mismatch of frameworks, which is as objective as any scientific constraint. General relativity predicts singular behavior, and quantum theory insists on fluctuations at small scales. We can estimate where the mismatch becomes unavoidable, and that estimate points to the Planck scale. It is one of the rare places in physics where dimensional analysis feels like a warning label. The Planck scale is not a wall we have observed directly, and we should be honest about that. It is a signpost that our current equations cannot both be right without modification, and it is derived from dimensional analysis with deep physical meaning. If we treat space-time as smooth down to arbitrarily small lengths, we ignore quantum uncertainty in geometry. If we treat geometry as quantum without a consistent theory, we lose predictive power. Either way, the classical singularity is not a satisfying endpoint. The cliff is real in the math, but the landscape beyond it is still unmapped. So what should we say carefully about nothing before the Big Bang, without turning caution into evasion? We should say that classical time may have a boundary in our best classical theory, and that boundary is what the singularity represents. We should say that the boundary is likely where quantum gravity becomes essential, because the Planck scale marks the collision of our frameworks. We should say that without quantum gravity, nothing may simply mean our equations stopped. That is not a final answer, but it is an honest one. It also keeps the question scientific, because it points to what must be improved. We can also say what we do not mean, because clarity often comes from exclusions. We do not mean that physics has proven absolute non-being, as if the universe came from a literal absence of reality. We do not mean that there was a literal empty void and then a sudden appearance of everything, like a stage waiting behind a curtain. We do not mean that the singularity is a confirmed physical point with infinite density. We mean that the classical model cannot be trusted arbitrarily far back. The difference is subtle in conversation, yet enormous in meaning. This is also where popular language about creation from nothing becomes slippery, because the word nothing shifts under our feet. In some physics contexts, nothing means a vacuum state, the lowest energy configuration of fields. That vacuum is not philosophical nothing, because it has structure, laws, and fluctuations, and it can store energy in subtle ways. In other contexts, nothing means the absence of space-time itself, which is a deeper claim that current physics cannot yet formalize cleanly. The same word is doing two different jobs, and the confusion is almost guaranteed. So the documentary's central question splits into two questions that sound similar but are not. Did the universe emerge from a quantum vacuum, which is a kind of something with fields already defined? Or did space-time itself emerge from a more primitive description where space and time are not fundamental variables? Both possibilities are studied, and neither is settled. The unsettling observation is that either answer would force us to revise what we mean by existence in physical terms. When we say time begins, we also have to ask what begins means in a theory, because beginnings can be coordinate dependent. In classical cosmology,
the scale factor goes to 0 at a finite proper time in the past, and that looks like a beginning. Yet it is produced by extrapolation beyond tested regimes, and it relies on smooth geometry all the way down. In a quantum gravity theory, the scale factor might never reach 0, or time might be replaced by another parameter. The beginning could be a feature of the model's coordinates, not a feature of the world. Some candidate ideas illustrate the range without resolving it, and they do so by altering the meaning of the boundary. A bounce model replaces the singularity with a minimum size, then re-expands, so the beginning becomes a turning point. An emergent time model treats time as a macroscopic parameter that appears only when certain degrees of freedom behave collectively. A no-boundary proposal replaces a sharp beginning with a smooth geometry, where time becomes space-like near the origin. In each case, the question, "What happened first?" is replaced by a question about what counts as time at all. These are sketches, not conclusions, and the documentary should keep them in that category. Their value is not that they solve the problem, but that they demonstrate how the question can be reframed. They show how before can be redefined rather than answered, and how a boundary can become a transition. They also remind us that the deepest unknown may be conceptual, not merely computational. If our best theories disagree about the stage, then even the meaning of evidence becomes more delicate. What unites them is the claim that the singularity is not the final word. The singularity is a symptom, and the cure is a theory that quantizes gravity or replaces space-time with something deeper. That is why quantum gravity is not a niche topic here. It is the missing bridge between our successful rewind and the question of ultimate origin. Without that bridge, we can describe the approach to the cliff in exquisite detail, but we cannot say what lies beyond. We should also keep the discipline learned from the CMB chapter, because speculation must remain tethered to measurement. The CMB pins down parameters and initial conditions for the later universe with remarkable precision, including the spectrum of primordial fluctuations. Any proposed new physics must reduce to standard cosmology where the data demand it. The earliest time ideas are constrained by the fact that the later time universe is measured. Even a radical beginning has to grow into the universe we actually see. So the mystery is bounded on both sides, like a canyon with firm rock walls and an unseen floor. On one side, singularities show us where classical theory fails, and they do so in a mathematically rigorous way. On the other side, the CMB and nucleosynthesis show us what must be reproduced after the earliest era. The unknown is real, but it is not unconstrained. That is what makes the problem scientific rather than purely philosophical. The question is not whether we can imagine an origin, but whether an origin model can survive contact with data. Now we return to the north of the North Pole analogy with a more careful role. It is not a way to dismiss the question, and it is not a smug trick of words. It is a way to warn that the grammar of the question may need revision, because physics sometimes changes what questions can mean. If time is emergent or bounded, then before may not be a meaningful coordinate. The right question might be about what replaces time near the boundary. And once you accept that, the mystery becomes sharper, not softer. Even if before is ill-posed, we still want a description of the earliest regime, because cosmology is judged by what it can predict. We want a model that predicts observable consequences, like a pattern of primordial fluctuations and their statistical properties. We want a model that explains why the universe is so uniform on large scales and why it is so close to flat. We want a model that turns quantum uncertainty into measurable structure. The remarkable twist is that the smallest scales may have left the largest fingerprints. This is where the next major idea enters, because it reshapes the earliest moments without claiming to solve everything. Cosmic inflation proposes a brief era of ultra-rapid expansion in the very early universe, driven by an energy component with negative pressure. In many versions, inflation stretches space exponentially, smoothing curvature and diluting unwanted relics. It also amplifies quantum fluctuations into classical density perturbations that later seed galaxies. Inflation is not introduced as a magic reset button, but as a dynamical mechanism with specific consequences we can hunt for. For visuals, the shift is dramatic. The cosmic grid does not merely expand, it surges outward so quickly that regions once microscopic become astronomical. Tiny ripples, initially quantum and jittery, are stretched into vast waves that later appear as temperature variations in the CMB. The scene can be quiet and eerie because inflation is not an explosion with debris. It is space itself swelling, as if the ruler used to measure it is being pulled apart. The horizon, what can communicate with what, seems to rearrange itself as the expansion outruns ordinary intuition. Inflation does not automatically answer what came before it, and it does not automatically remove the need for quantum gravity. Some inflationary models still begin with a singularity, and some attempt to avoid one by changing the earliest conditions. But inflation changes what we mean by the beginning, because it can hide earlier conditions behind an enormous expansion. It can make the observable universe insensitive to what came before, even if something did. That raises a haunting question. If earlier history is erased, what kind of evidence could ever reveal it? So the chapter ends with a shift in perspective rather than a final claim. The singularity is a mathematical cliff that tells us our current map ends, and it does so with the authority of a theory that has passed every test we have thrown at it. The Planck scale marks where the cliff is expected, because quantum gravity should matter there. The before problem warns us that time may not extend past the boundary in the usual way. The closer we stare at the edge, the more we realize the edge is drawn by our concepts as much as by the cosmos. Without new physics, nothing before the Big Bang can be a mirage created by extrapolation, a word we use when our coordinates fail. With new physics, the boundary might become a transition, a bounce, or an emergent beginning where the word before must be rewritten. Either way, the mystery is not empty space. It is the edge of our concepts. And the most honest narration is one that lets that edge remain sharp. Next, we follow the idea that most dramatically reshapes the earliest timeline. Inflation is an expansion so rapid that it can erase traces of earlier history, while leaving a faint statistical signature in the sky. If singularities mark the limits of classical space and time, inflation shows how early dynamics can hide what came before. We step into that era, where the universe grows faster than intuition, and where the origin story becomes both clearer and stranger. We left Chapter 4 at a cliff edge where classical space-time stops extending cleanly backward, and where the equations begin to signal their own limits. Inflation enters as a proposed bridge across that edge, not as a proven fact. It is a mechanism that can explain what the CMB hints at, while also deepening the central question. What, if anything, could have existed before the Big Bang? And what do scientists mean by nothing? Inflation begins as a motivation problem, not a particle or a slogan, and historically it emerged from discomfort with coincidences. In the late 1970s, cosmologists had a hot Big Bang model that worked well, yet it seemed to require strangely special starting conditions. The CMB is smooth to 1 part in 100,000 across the entire sky, and that smoothness is not a vague impression. It is a quantitative statement about temperature variations measured in microkelvin, mapped with satellites that turn the whole sky into data. In standard hot Big Bang expansion without inflation, that smoothness looks suspiciously coordinated across angles that were never able to exchange signals. Regions on opposite sides of the sky appear too uniform, given the limited time light had to travel between them. That mismatch is called the horizon problem, and it is a problem about causal contact, not about telescope reach. It asks a simple question in a technical language. How did distant regions learn to agree? At recombination, the universe was about 380,000 years old in the usual timeline, and the plasma cooled enough for electrons and protons to form neutral hydrogen. When that happened, Photons stopped scattering constantly and began to stream freely. And that streaming is what we see as the CMB.
Light could only have crossed a finite distance since the hot phase began, because the expansion history sets a strict causal budget. Yet the CMB temperature is nearly the same in directions that were apparently never in communication. If the early universe was a patchwork of disconnected regions, why did they settle on the same temperature and the same photon-to-baryon ratio? Why did they share the same thermal story, down to the same blackbody spectrum with tiny, patterned departures? The horizon problem is not about what we can see today, but about what could influence what back then. It is about the size of the particle horizon in a decelerating expansion, where the co-moving horizon grows and distant regions remain strangers. It is also about whether thermal equilibrium could have been established across the whole visible sky, because equilibrium is not magic. It requires interactions, scattering and time, and it leaves fingerprints like uniform temperature and a clean Planck spectrum. The CMB's uniformity looks like a universe that had time to mix, then later expanded. The basic hot Big Bang gives expansion and cooling, but it does not provide enough early mixing across the entire region that later becomes our observable sky. A second motivation is geometric, and it sounds abstract until you translate it into numbers that evolve under the Friedmann equation. The CMB power spectrum indicates the universe is very close to spatially flat, meaning the spatial curvature parameter is consistent with zero within tight uncertainty. Flatness here means the curvature term in the Friedmann equation is tiny today, compared with the energy density terms. In the standard decelerating history, any small deviation from flatness grows with time, because curvature dilutes more slowly than radiation or matter in the relevant variables. That makes today's near flatness look like an extreme fine-tuning of initial conditions, as if the early universe had to be balanced on a knife edge. The flatness problem is a stability question, and it is a question about dynamical sensitivity. If the early universe started even slightly curved, decelerating expansion would amplify that curvature relative to the energy density. To land on a universe that still looks flat after billions of years, the initial curvature must be tuned to extraordinary precision, far beyond what feels natural without a mechanism. Inflation proposes a dynamical reason for that precision, rather than an unexplained coincidence that is simply assumed at the start. It turns flatness into an attractor, at least for the observable patch, by changing how the scale factor evolves. Instead of curvature gradually winning in the bookkeeping, accelerated expansion makes curvature rapidly irrelevant. The universe does not need to begin perfectly flat everywhere. It needs an era that drives the local geometry toward flatness. A third motivation comes from particle physics expectations, and it is a disappearance act with a long history in grand unified thinking. Many grand unified theories predict magnetic monopoles, heavy relics associated with symmetry breaking in the early universe, and their existence would be profound. If they were produced abundantly in a hot beginning, they should still be around today because they are stable and massive. We do not see them, despite serious searches in cosmic rays, in matter samples, and in dedicated detectors. This is the monopole problem, and it is about unwanted relics surviving the early furnace, when theory naively says they should not be rare. Inflation addresses all three motivations with one basic move, and that economy is part of its appeal. It inserts a brief era of accelerated expansion very early in cosmic history, before the familiar radiation-dominated cooling. During that era, the scale factor grows nearly exponentially, or at least fast enough to mimic exponential behavior over many e-folds. Distances between co-moving points grow so rapidly that causal horizons behave differently, and the bookkeeping of what can influence what is rewritten. Curvature is diluted, and heavy relics are diluted too, because number densities fall as volume expands. The core idea can be stated without metaphors, and it must be stated carefully to avoid the most common misunderstanding. Inflation is not galaxies flying through space faster than light, because galaxies are not even formed yet in that era. It is space itself expanding, So the distance between far-apart points can increase faster than light could traverse that distance. This does not violate special relativity because relativity limits motion through space locally, in the neighborhood of any observer. General relativity allows the metric to evolve so that global separations grow superluminally, and the speed limit applies to local measurements, not to the growth of the scale factor. Visually, this is a subtle kind of motion, because nothing needs to push through space. Imagine a grid drawn on a flexible sheet, and imagine the sheet stretching, so the grid squares widen everywhere at once. The points are not sprinting across the sheet, yet their separation grows, and that separation is what matters for causal contact. Inflation is that kind of stretching, but encoded in the geometry of space-time itself. Inflation changes the causal story behind the CMB, and it does so by rearranging the timeline of contact. Before inflation ends, the region that becomes our observable universe can be small enough to have been in causal contact, even if it later becomes enormous. It can thermalize, equalize temperatures, and settle into a uniform state through ordinary interactions. Then inflation stretches that once connected region to an enormous size, far larger than the horizon that would exist in a purely decelerating history. After inflation, the hot Big Bang resumes. But it begins from a smoothed, flattened patch, and the CMB's uniformity becomes a memory of pre-inflation contact, hidden behind later expansion. Inflation also changes the curvature story behind flatness, and the mathematics is more direct than the analogies suggest. Exponential expansion drives the curvature term toward zero, in the same way that a rapidly inflating balloon looks flatter on any small patch, even though the whole surface remains curved. The analogy is limited, but the math is clear in the Friedmann equation. When accelerated expansion holds, the energy density associated with the inflationary component dominates over curvature, and the ratio that measures curvature is driven toward zero. The result is that many different initial curvature values evolve toward near flatness within the inflated region, so flatness becomes less of a miraculous initial setting and more of an outcome. Inflation changes the relic story behind monopoles by brute dilution, and dilution is a simple but powerful tool. If monopoles were produced before inflation, their number density is stretched away as the volume grows by an enormous factor. After inflation, the universe reheats, but the temperature may not return to the monopole-producing regime, depending on the reheating scale. Even if it does, the production can be suppressed by the details of symmetry breaking and the thermal history. The key point is that inflation provides a reason we might not see relics that naive hot beginnings would overproduce. This is the first major transition in the chapter. Inflation is introduced as a fix for puzzles that the CMB and basic expansion make unavoidable. It is a proposed early phase that reshapes what initial conditions even mean, because it can make many starting details observationally irrelevant. But inflation is not only a smoothing machine, and that is where it becomes more than a patch. It also claims to explain the opposite feature of the CMB, the tiny anisotropies that seed structure, because a universe that is perfectly smooth stays perfectly smooth. We need imperfections, but we need them in a very specific statistical form, because the later universe is not chaotic in an arbitrary way. The galaxies trace a pattern that looks like amplified early noise, and the CMB encodes that noise before gravity fully takes over. The scientific detail begins with a simple statement, and it is one of the strangest in modern physics. Quantum fields fluctuate even in their lowest energy states because the uncertainty principle forbids exact stillness in conjugate quantities. These fluctuations are not optional, and they are not artifacts of measurement because they appear as real correlations in the vacuum state. In ordinary settings, they remain microscopic and average out, and their effects are usually subtle. During inflation, the rapid expansion stretches them to macroscopic scales, and tiny quantum variations become large-scale perturbations in density and curvature. The key step is horizon crossing, described in the language of inflationary perturbation theory, where the geometry sets the rules of freezing and thawing. During accelerated expansion, The Hubble radius behaves differently than in decelerating eras, and the co-moving Hubble radius can shrink.
Modes that start well inside the horizon are stretched until their wavelengths exceed the horizon scale. When that happens, the fluctuations effectively freeze in amplitude, not because dynamics stop, but because causal microphysics can no longer keep the mode oscillating coherently. Later, after inflation ends and normal expansion resumes, those modes re-enter the horizon, and they return as classical-looking perturbations that concede acoustic oscillations and later structure. This is how inflation links quantum mechanics to the CMB power spectrum, and it is a rare bridge between the very small and the very large. The CMB anisotropies are not random blotches with arbitrary statistics, and the pattern is not merely aesthetic. They are consistent with a nearly scale-invariant spectrum of primordial perturbations, meaning the fluctuation power changes only slowly with scale, with a slight tilt. Inflation naturally produces such a spectrum in many models, because the expansion rate is nearly constant while modes exit the horizon, and the slow drift from exact constancy becomes the tilt. The measured spectral index is close to, but not exactly, 1, and that near 1 value is a major empirical clue about the inflationary dynamics. Inflation also predicts approximate Gaussianity, which is a technical way of saying the primordial field is close to simple random noise, with a specific symmetry. In the simplest slow-roll models, the perturbations are close to a Gaussian random field, so their statistics are largely captured by the two-point correlation function, or equivalently the power spectrum. Higher-order correlations exist, and they matter because they encode interactions and non-linearity in the inflationary era. Non-Gaussianity can be larger in more complex models, but it is constrained by data, and the current CMB measurements show the fluctuations are very nearly Gaussian. That supports the simplest inflationary mechanisms, and it also narrows the space of alternatives without proving any single model. Inflation's success is therefore not only qualitative, because it lives in the numbers. It makes quantitative predictions that can be tested, and many have been tested with increasing precision since the first Kobe maps and the later WMAP and Planck surveys. The near-scale invariant spectrum is measured, and the acoustic peak structure is consistent with adiabatic initial conditions, which inflation often produces. The phase coherence of peaks fits the idea of primordial perturbations laid down early, then evolving linearly in the photon-baryon fluid. These are not aesthetic wins, but statistical matches between theory and sky. Matches that survive cross-checks, calibration battles, and independent experiments. Yet the chapter must keep the tension alive because inflation is still a hypothesis about an era we cannot observe directly. The CMB is a wall for photons, and it is a remarkably sharp one, because earlier photons are scattered and thermalized into the same last scattering surface. Inflation is earlier than recombination by an enormous factor, and it operates at energies far beyond laboratory reach. We infer inflation by reading patterns in the CMB, not by watching inflation happen, and that inference is powerful but indirect. The central question remains, because indirect evidence can constrain, but it rarely closes every door. To sharpen the tension, we introduce what drives inflation in the models, and we do it with the minimum machinery needed. Inflation is typically modeled with a field, often called the inflaton, and it is treated as a scalar field with a potential energy that dominates the energy density. When the potential energy dominates, the pressure becomes negative enough to drive accelerated expansion, and this is a general relativity statement. In GR, pressure gravitates, so the sign and magnitude of pressure matter for cosmic acceleration. Negative pressure can produce repulsive gravitational behavior in the expansion equations, even though locally gravity remains attractive in the usual sense. The inflaton must be introduced with restraint, because the name can sound more concrete than the evidence warrants. It is not a confirmed particle in the standard model, and it is not something we have detected in a collider. It is a placeholder for a dynamical ingredient that produces the right expansion history and perturbations, and many different potentials can produce inflation-like behavior. Some models tie the inflaton to known fields like the Higgs, but those identifications are speculative and constrained by particle physics data. The inflaton is therefore a useful model, not a discovered object, and that distinction matters when we talk about origins. The slow roll condition is the technical heart of many inflationary models, and it is a balance between steepness and friction. The field rolls slowly down its potential, so the energy density remains nearly constant for a time, and the expansion acts like a damping term that keeps the roll gentle. That near constant energy density yields quasi-exponential expansion, which is what the horizon and flatness puzzles require. Slow roll also controls the perturbation spectrum, linking the tilt and amplitude to the shape of the potential. This is where inflation becomes predictive, because the same parameters that drive expansion also shape the fluctuations we later measure. Inflation must end, or it would prevent the hot Big Bang from ever beginning in the usual sense, with radiation, particles, and nuclear reactions. The end is called the end of inflation, but the more important process is what follows, because it is the handoff to known physics. The inflaton's energy must be converted into ordinary particles and radiation, and that conversion is reheating. Reheating repopulates the universe with a hot plasma, and it sets the initial conditions for the standard hot Big Bang evolution that leads to nucleosynthesis and later recombination. Reheating is not a decorative epilogue because it connects inflation to the evidence we already trust, like light element abundances and the thermal history implied by the CMB. If reheating fails, inflation would not lead to the observed radiation-dominated era, and the successes of standard cosmology would be lost. The details of reheating affect the temperature reached, the production of particles, and possibly relic signatures that could matter later. Reheating is model-dependent, and it is one of the places where inflation remains uncertain, because it depends on couplings we do not know. Still, the broad requirement is clear. Inflation must hand the universe back to a hot, dense state that matches known early universe physics. Now the chapter returns to tests, because inflation lives or dies by predictions that can be compared with the sky. One major prediction is the existence of primordial gravitational waves, and this is where the story becomes especially visual. Quantum fluctuations are not only in scalar density modes, but also in tensor modes, ripples in space-time itself. Inflation can generate a stochastic background of gravitational waves, with a spectrum tied to the inflationary energy scale. And those tensor modes would leave an imprint on the CMB polarization. They would produce a distinctive B-mode pattern at large angular scales, a curl-like signature that cannot be made by density perturbations alone. The hunt for primordial B-modes is therefore a hunt for inflation's energy scale, and it is also a test of whether the inflating state was energetic enough to shake space-time measurably. A detection would be a major confirmation that accelerated expansion occurred at very high energies, and it would constrain the inflaton potential and the dynamics of the early universe. But the search is hard, because B-modes are faint and contaminated by foregrounds that are bright and structured. Dust in our galaxy can mimic the signal, and gravitational lensing converts E-modes into B-modes at smaller scales, creating a secondary background that must be modeled and subtracted. Experiments must separate these contributions with extreme care, using multiple frequencies, careful calibration, and statistical cross-checks. So far, the result is a set of upper limits, not a definitive detection, and those limits already shape the theory landscape. They rule out some simple high-energy inflation models that predict large tensor amplitudes, and they push viable models toward lower tensor to scalar ratios, or toward mechanisms that suppress tensor modes. The non-detection is still information, because it prunes the theory space and forces more precise model building. It also keeps the story open, because the key signature remains just out of reach, hovering at the edge of instrumental sensitivity. Inflation is therefore in a peculiar scientific position, and the documentary should let that ambiguity feel earned rather than frustrating. It is strongly motivated by multiple problems, and it matches key features of the CMB with impressive accuracy. It has a framework that generates testable predictions, and many predictions are consistent with data across temperature maps, polarization, and large-scale structure. Yet it is flexible enough that many versions survive, and some versions are difficult to falsify with foreseeable observations. That flexibility is both a strength and a weakness, because it means inflation is a paradigm, not a single theory with a single parameter set. This is where the narrative stakes rise, because inflation changes the meaning of beginnings in a way that is easy to say and hard to absorb. In the standard hot Big Bang story, the beginning is the hot, dense state, then expansion and cooling, and the earliest evidence is the CMB. Inflation says that hot, dense state may be a reheated aftermath, not the earliest phase, and that the hot Big Bang is a chapter that begins after something else. It pushes the start of the hot Big Bang later than the start of the universe's expansion history, and it relocates the word beginning from a temperature condition to a dynamical transition. Inflation also raises the possibility that what we call the beginning is local, not global, and that is where the imagery becomes almost unsettling. In many models, inflation can be eternal to the future, and possibly to the past in some sense, depending on assumptions. Quantum fluctuations of the inflaton can keep inflation going in some regions, while it ends in others, like a landscape where some valleys settle while other ridges keep rolling. Where it ends, reheating occurs, and a hot Big Bang region begins. Those regions are sometimes described as bubble universes or pocket universes, embedded in a larger, inflating background. The phrase eternal inflation must be handled carefully, because it is not a single settled claim with one agreed mechanism. It is a class of scenarios that arise in some potentials and parameter regimes, and it depends on how quantum fluctuations compete with classical slow roll. It suggests that inflation does not end everywhere at once, and may never end globally, even if it ends locally in many places. That would mean our observable universe is one reheated patch in a much larger space-time. And in that picture, beginnings are not unique global events. They are local transitions, repeated many times, with each transition producing its own hot, expanding region. This possibility deepens the central question rather than resolving it, because it replaces one beginning with a hierarchy of beginnings. If our hot Big Bang is a local reheating event, what existed before that event in our region, and what determined the conditions of the inflaton field there? What set the inflaton field and its potential, and why did it start in the state that allows slow roll rather than immediately ending? What started inflation in the first place, and why did it start in the particular configuration that makes our observable patch possible? The beginning is pushed back but not eliminated, and the mystery is displaced into the conditions that make inflation possible. Inflation also interacts with the singularity discussion from Chapter 4, and the interaction is not as comforting as popular summaries suggest. Some theorems suggest that inflationary spacetimes can still be passed incomplete under broad assumptions, meaning they cannot be extended indefinitely into the past along certain trajectories. That means inflation might not remove the need for an earlier boundary or earlier physics, even if it smooths and flattens what comes after. Even if inflation hides earlier conditions from observation, it may still require some earlier explanation, because smoothing is not the same as providing an origin. So inflation is both explanatory and evasive, depending on what question we ask. And that asymmetry is part of the documentary's theme. If we ask why the CMB is uniform, inflation offers a mechanism. If we ask why the universe is nearly flat, inflation offers a mechanism. If we ask where the perturbations came from, inflation offers a mechanism tied to quantum fluctuations, with statistical predictions that match the sky. If we ask why inflation happened at all, inflation often answers with another assumption about fields, potentials, and initial conditions. The documentary must let that imbalance be felt, because it is where cosmology becomes philosophy adjacent without leaving physics. Now we bridge explicitly back to the CMB as evidence, because this is where inference becomes a disciplined craft. The CMB power spectrum is the main arena where inflation is tested, and it is more than a curve on a plot. Each acoustic peak encodes a competition between gravity pulling matter in and radiation pressure pushing it out, and the pattern depends on the initial phases of oscillation. The tilt of the spectrum, the lack of large non-Gaussianities, and the adiabatic nature of perturbations all point toward inflation-like initial conditions, and they do so consistently across datasets. The polarization data add constraints on reionization and lensing, and they refine the parameter fits, tightening uncertainties and exposing tensions. Each new dataset tightens the net around early universe models, yet the net still has holes large enough for multiple inflationary stories to slip through. We also reconnect to the earlier promise of other messengers, because cosmology advances by finding ways around observational walls. Primordial gravitational waves would be a messenger from inflation, not blocked by the photon wall, because gravitational waves propagate with extremely weak coupling. A relic neutrino background would be an even earlier messenger, though far harder to detect, because neutrinos decouple when the universe is seconds old. These messengers are not narrative decorations, because they represent a strategy. If photons stop at recombination, we look for signals that decouple earlier or interact more weakly. Inflation becomes testable not by direct viewing, but by indirect fossils preserved in polarization, in correlations, and in the statistical texture of the sky. At this point, the chapter pivots toward nothing, because inflation is often described with vacuum language that can mislead without careful definitions. The inflaton field during inflation behaves like a vacuum-like energy component, meaning it has an energy density that changes slowly and exerts negative pressure. It has energy density even when there are no particles in the usual sense, and it drives expansion through its stress energy in Einstein's equations. It also fluctuates quantum mechanically, and those fluctuations are the seeds of everything we later call structure. That means the engine of inflation is not matter in the everyday sense, with atoms and radiation. It is a field configuration of what we casually call empty space. This is where the documentary must tighten its definitions, because the word vacuum carries everyday baggage. In physics, vacuum does not mean the absence of everything, like an empty box with nothing inside. It means the lowest energy state of a field, given the laws and the background. And that state can still have non-zero energy. It can have fluctuations, and it can have structure, like correlations and virtual excitations, even when no particles are present. Inflation relies on that kind of vacuum-like state, which is a kind of something, even if it looks like nothing to common sense. So when people say inflation suggests the universe came from nothing, we have to ask which nothing they mean, because the word hides multiple concepts. If they mean no particles, inflation can begin with a field-dominated state that is nearly empty of particles, and then reheating fills it with a hot plasma. If they mean no space and no time, inflation does not automatically provide that, because inflation is a process that occurs in space-time and is described by fields on a background geometry. It presupposes a stage, even if the stage is rapidly changing, and it presupposes laws that tell the stage how to evolve. Still, inflation pulls us closer to the boundary where everyday emptiness fails, and it does so with unsettling elegance. It places quantum fields at the center of the origin story, and it suggests that what looks like empty space can carry energy that shapes cosmic history. It suggests that fluctuations in that empty state can become the blueprint for galaxies, clusters, and the web of matter. It turns vacuum from a passive absence into an active source of structure, and it makes the universe feel less like a machine that starts and more like a system that transitions. This is the second major transition in the chapter. Inflation solves practical cosmological puzzles, then forces us to confront what counts as emptiness in physics. The closer we get to the beginning, the more nothing starts to look like a quantum state with rules, and the more the word empty becomes a technical term rather than a feeling. We also have to acknowledge the open problems without turning them into a collapse of confidence, because uncertainty is part of the honest story. We do not know the identity of the inflaton, if it exists, and we do not know whether it is a new field or an effective description of something deeper. We do not know the exact shape of its potential, though data constrain broad classes through the spectral tilt and limits on tensors. We do not know the detailed reheating mechanism, though it must reproduce a hot plasma that leads into nucleosynthesis.
We do not know whether inflation was a single event or part of a larger, eternal process with many reheating regions. These are not minor gaps, because they determine whether inflation is a unique explanation or one option among many. There is also a methodological tension that mirrors the documentary's central theme, and it is almost poetic in its logic. Inflation can make the observable universe insensitive to pre-inflation conditions because it stretches away information and drives many variables toward attractor behavior. That is part of why it solves the horizon and flatness problems and why it makes the universe look forgetful. But that same erasure can make it harder to learn what came before inflation, because the evidence is diluted along with the relics. If inflation wipes the slate clean, then the earliest questions become harder to test. And the theory that explains why the universe looks forgetful might also explain why we cannot recover its earliest memory. So the chapter ends by holding two truths together, without forcing them to reconcile too quickly. Inflation is one of the most successful ideas in early universe cosmology, because it connects multiple puzzles to one dynamical phase and predicts the statistical form of primordial perturbations. Inflation is also a doorway to deeper mysteries, because it shifts the beginning earlier and makes it more abstract. It replaces a hot beginning with a vacuum-like phase, then a reheating transition, and it replaces a single origin moment with the possibility of local beginnings in a larger reality. We return to the opening hook, now sharpened by the inflation story and by what it implies about emptiness. If we rewind past every galaxy, past every atom, past light itself, we do not reach simple emptiness. We reach fields, vacuum energy, and quantum fluctuations that refuse to be truly still, even in their lowest energy states. The closer we get to the beginning, the more the word before depends on which model of spacetime we trust, and on whether time itself has a boundary. The closer we get to nothing, the more nothing behaves like a physical state with structure. Next, we follow that vacuum idea into its most unsettling form. We ask what quantum field theory says about empty space and what it means to say that nothing can fluctuate. We move from inflation's cosmic expansion to the quantum vacuum that could underwrite it, where the language of absence becomes the language of fields. The wall of the CMB remains behind us, but the deeper wall is conceptual. It is the boundary where emptiness stops meaning what we think it means. We keep rewinding past inflation's handoff, and the word empty stops behaving the way our instincts expect. The closer we drift toward the earliest moments, the more nothing becomes a technical term rather than a casual description. The central question returns with sharper edges, as if the universe is daring us to define our terms precisely. What, if anything, could have existed before the Big Bang? And what do scientists mean when they say, nothing? In everyday language, nothing is a void with no stuff inside it, a blank container with the lights turned off. We picture an empty room after the furniture is removed, or a dark sky with no stars. That intuition is powerful because it matches how objects behave at human scales. Yet modern physics learned step by step that space is not merely a stage where matter performs. In quantum field theory, nothing is closer to a vacuum state, meaning the lowest energy state of fields. The word field here is not poetic. It is a measurable entity assigned to every point in space and time. Electromagnetism is a field, and so are the electron field and the quark fields, even when no particles are present. In this picture, particles are not fundamental beads. They are localized excitations of underlying fields. That vacuum is not the absence of fields, because the fields are the underlying ingredients that cannot be removed without changing the theory itself. It is a particular configuration of those fields, defined by the laws and the background geometry. Even the phrase lowest energy depends on what counts as energy, and energy depends on symmetries of space-time. The vacuum is therefore not just emptiness. It is a state carefully defined by mathematics and by the structure of the universe.
A vacuum state can look featureless at human scales, yet it still carries structure that experiments can interrogate. It contains correlations, it can store energy, and it supports fluctuations that cannot be switched off by any clever engineering. The uncertainty principle forbids exact stillness in conjugate quantities, even in a ground state. So the vacuum is not a calm emptiness. It is a minimum that still jitters. To visualize this, imagine a perfectly still ocean seen from far above, where the surface looks flat and quiet. Now lower the camera to the waterline, and the surface becomes restless with tiny ripples. In quantum theory, the ripples are not caused by wind or passing boats. They are built into the rules that connect what can be known to what can be measured. We should be precise about what fluctuation means in this context, because the popular imagery can mislead. It does not mean particles popping in and out like tiny fireworks in a literal empty box. That picture can be a helpful metaphor, but it breaks if taken too literally. It means the field's measurable quantities have irreducible quantum spread, even when no particles are present. Particles are excitations above the vacuum, while the vacuum itself is the baseline state. In many cases, that baseline is defined by annihilation operators acting on the vacuum to give zero, which is a formal way to say there are no quanta present. Yet the field operators still have non-zero fluctuations in that state. The vacuum is quiet in one sense and restless in another, and the difference matters. Historically, this shift in meaning did not arrive all at once. Early 20th century physics still pictured atoms as miniature solar systems and space as a passive arena. Then came quantum mechanics, and with it the realization that ground state does not mean motionless. Even a harmonic oscillator at absolute zero retains zero-point energy, a residue that cannot be extracted without violating the uncertainty principle. The vacuum inherits that lesson and generalizes it to every field. This is the first pivot of the chapter. Nothing in physics is already a kind of something. It is a state of fields obeying rules, not the philosophical idea of absolute non-being. That distinction can feel like wordplay until we remember what physics is allowed to talk about. Physics describes states within a framework, and the framework itself is part of what nothing quietly assumes. The claim that empty space has effects is not only theoretical, and we can point to clean examples that do not rely on cosmology. The first is the Casimir effect, described without math but with a clear logic. Two uncharged conducting plates placed very close can experience an attractive force. The effect is tiny, but it is real and measurable with careful apparatus. To picture it, imagine two mirror-like plates facing each other in a vacuum chamber, separated by a gap thinner than a human hair. Around them is a larger volume of empty space, seemingly identical to the gap. Yet the plates impose boundary conditions on the electromagnetic field, restricting which wavelengths can fit between them. Outside the plates, the field can support a richer spectrum of modes. The force arises because the allowed vacuum modes between plates differ from those outside. In a simplified description, fewer modes inside means a different vacuum energy density than the region outside. Nature responds by pushing the plates toward the configuration with lower total energy. The plates are not attracted because they are charged. They are attracted because the vacuum's structure is altered by geometry. The Casimir effect is not a proof that the vacuum is made of particles, and it does not require us to imagine a literal sea of popping quanta. It is evidence that the vacuum state depends on boundaries and geometry, and that difference is measurable. It shows that empty space has physical degrees of freedom that respond to constraints. The vacuum, in other words, can be engineered. There is also a deeper lesson hiding in this tabletop phenomenon. The vacuum is not a single universal object independent of context. Change the boundary conditions, change the state that counts as lowest energy, and the physical consequences change with it. That sensitivity will matter later, when we ask what the vacuum means in a dynamical space-time. A second line of evidence is the Lamb shift, a real shift in atomic energy levels that was historically pivotal.
hydrogen's levels split in a way that cannot be explained by the simplest Dirac picture alone. In the late 1940s, precise spectroscopy revealed a small discrepancy, and it demanded a new level of theoretical honesty. Quantum electrodynamics, QED, rose to meet that demand. Quantum vacuum fluctuations and radiative corrections contribute to the observed shift.
In intuitive terms, the electron in a hydrogen atom does not move through a silent background. It interacts with the electromagnetic field even in its vacuum state, and that interaction slightly alters the electron's effective energy. The effect is subtle, but it is repeatable, and it matches calculations once renormalization is handled correctly. So the vacuum influences matter not only in exotic setups, but inside ordinary atoms. The same empty space between the proton and electron is not empty in the classical sense. It is a field environment with quantized behavior, and the atom is sensitive enough to notice. When we say the vacuum has structure, we are not speaking metaphorically. We are describing a measurable contribution to the spectrum of hydrogen. A third effect is vacuum polarization, kept at a high level but stated plainly.
In quantum electrodynamics, the vacuum behaves like a medium that can be polarized by charges. A charged particle does not sit in a perfectly transparent emptiness. Instead, the surrounding vacuum responds, modifying how the electric field spreads through space. That polarization slightly screens electric charge at longer distances, changing effective coupling with scale. At shorter distances, the screening is reduced, and the effective charge appears stronger. This running of the coupling is a cornerstone of modern quantum field theory, and it is tested in high-energy scattering experiments. It is another way the vacuum acts like an active participant, not a passive background. These effects matter for our story because they anchor the vacuum in evidence. We are not invoking nothing as poetry or as a convenient mystery word. We are invoking a state whose influence has been measured, modeled, and used to predict new results. The vacuum is strange, but it is not arbitrary. Now we widen the frame from laboratory to cosmos, because the vacuum also gravitates. In general relativity, energy and pressure contribute to curvature, and vacuum energy is no exception. Gravity does not only respond to mass in the everyday sense. It responds to the stress-energy tensor, which includes energy density, momentum flow, and pressure. A vacuum-like component has negative pressure, and that combination can drive accelerated expansion. In the simplest case, vacuum energy density stays constant as space expands, which is profoundly unlike matter or radiation. Matter dilutes as volume grows, and radiation dilutes even faster because its wavelength stretches. Vacuum energy, in contrast, is tied to space itself. So more space means more total vacuum energy. This is the same basic logic that made inflation plausible in the previous chapter. A nearly constant energy density can cause the scale factor to accelerate, smoothing and flattening the observable region. In the inflationary story, the vacuum-like state is not necessarily the true lowest energy vacuum. It can be a metastable configuration, a false vacuum, whose energy temporarily dominates. In today's universe, we see a late-time acceleration in the expansion rate. The simplest description is a cosmological constant, a constant vacuum energy density filling space. In Einstein's equations, it behaves as energy of space itself, not energy diluted by expansion. Observations of supernovae, large-scale structure, and the CMB support this accelerated expansion. Visually, the evidence reads like a faint but persistent curve on a cosmic graph. Distant supernovae appear dimmer than they would in a decelerating universe, implying extra expansion has occurred while their light was in transit. Galaxy clustering patterns carry the imprint of how expansion competed with gravity over billions of years. The CMB provides a geometric anchor, setting the stage on which these later measurements make sense. Here the chapter reaches a hard tension that physics has not resolved, and we should not pretend it is merely technical.
Quantum field theory naively predicts enormous vacuum energy from zero-point contributions. If one sums the ground state energies of field modes up to very high frequencies, the result explodes. General relativity says that energy should gravitate and curve space-time dramatically. Yet the observed dark energy density is tiny compared to those naive estimates. The mismatch is not a factor of 2 or a missing minus sign. It is an abyss of scales, often summarized as the worst theoretical prediction in physics.
Even if we treat the cutoff as a placeholder for unknown high-energy physics, the discrepancy remains unsettling. This mismatch is the cosmological constant problem, and it is not a small bookkeeping error. It is a clash between our best quantum description of fields and our best classical description of gravity. It suggests either cancellations we do not understand, new symmetry, new dynamics, or a new framework. It also warns us that vacuum energy is not a settled concept when gravity is included. There is also a historical echo here because physics has faced similar shocks before. The ultraviolet catastrophe forced a new theory of radiation, and Mercury's orbit forced a new theory of gravity. In each case, a small observational discrepancy revealed a deep conceptual flaw. The cosmological constant problem feels like that kind of warning sign. Quiet in the data, loud in the equations. So the vacuum is both solid and slippery. It produces measurable effects in controlled experiments, yet its absolute energy seems conceptually unstable in cosmology. That instability matters for origin stories, because many universe-from-nothing ideas lean on vacuum energy. If we do not fully understand vacuum energy with gravity, then our origin narratives inherit that uncertainty. Now we approach the chapter's central hypothesis space, and we label it clearly as hypothesis rather than conclusion. Some proposals suggest a universe could arise from a quantum process, like tunneling from a metastable state. In these scenarios, the vacuum is not an empty container waiting to be filled. It is the starting state within a theory, complete with fields and a rulebook. One class of ideas uses quantum tunneling language applied to cosmology. The claim is that a small closed universe could nucleate from a quantum transition, then expand. In ordinary quantum mechanics, tunneling allows a particle to cross a barrier without the energy to climb over it. In cosmology, the barrier is not a wall in space, but a barrier in configuration space, the space of possible geometries. The details vary, and the interpretation depends on how one defines a wave function of the universe. That phrase sounds like science fiction, yet it is a serious attempt to apply quantum principles to the entire cosmos. One must decide what counts as an observable, what counts as a boundary condition, and what counts as probability. Each choice shapes the story we tell. The key point is modest, even if the imagery is dramatic. Quantum theory allows transitions that have no classical trajectory. A process can be permitted by the rules even when it has no classical analog. If we are searching for an origin that avoids a classical singularity, quantum transitions are an obvious place to look. Another class of ideas is no-boundary style reasoning, framed cautiously and without claiming it is established. Instead of a sharp initial boundary in time, the geometry is smoothed, so the beginning is not a singular edge. Time can behave like a spatial direction near the origin, making earlier lose its usual meaning. The proposal aims to replace a hard beginning with a regular condition on the geometry. A useful visual analogy is a globe, where lines of longitude converge smoothly at the pole. Asking for a point north of the North Pole is not forbidden by geography, but it is undefined by the coordinate system. In the no-boundary picture, the start of the universe is more like that pole than like a cliff. The geometry closes off smoothly, and the demand for an earlier time becomes a category error. A third family is vacuum fluctuation scenarios that generate space-time domains. The vacuum can support field configurations that inflate, creating regions that become large classical universes. This resembles the logic of eternal inflation, but we keep the emphasis on what is assumed. It assumes quantum fields, a background rule set,
and a mechanism that turns fluctuations into expanding domains. Here, the visuals almost write themselves, even if the physics remains speculative. Picture a vast, dark expanse where nothing happens in the everyday sense, yet the underlying fields never become perfectly still. In rare patches, a fluctuation pushes a field into a configuration that behaves like a high-energy vacuum. That patch begins to expand rapidly, and its interior becomes a growing bubble of space-time. None of these ideas is a confirmed account of our beginning, and it is important to keep that boundary clear. They are attempts to use quantum principles to replace a classical singularity with a quantum origin or transition. They are also reminders that from nothing usually means from a vacuum state within a theory. That is not philosophical nothing. It is a physical baseline that already contains laws. This is the chapter's tension peak, and we hold it without resolving it too quickly. If physics nothing still contains fields, rules, and quantum structure, then what would absolute nothing even be? If absolute nothing means no space-time, no fields, and no laws, then our current methods cannot model it. Science can test models that produce predictions, and absolute nothing may be a boundary concept beyond testable structure. We return to the earlier warning about smuggling assumptions into the word nothing, because the word is doing too much work. When a model says nothing, it often means a specific state, plus a mathematical framework that defines it. The framework is doing heavy work, and it is easy to forget it is there. Even the ability to ask the question depends on a language of laws, states, and possibilities. So the honest question becomes two questions, and both are scientific in spirit. What is the lowest layer the model presupposes, and can that layer be tested? If the presupposition is a quantum field on a background geometry, we can ask what signatures it leaves. If the presupposition is a deeper quantum gravitational structure, we can ask what low-energy traces survive. The point is not to dismiss the models, but to keep our definitions visible. Now the chapter pivots to time, because origin claims live or die on what before means. If time itself began, then before the Big Bang might not be a meaningful phrase. This is not a rhetorical dodge, and it is not an attempt to protect a mystery. It is a statement about how time is defined in physics. In relativity, time is not an external universal parameter ticking outside the universe. Time is part of space-time geometry, and it is measured by physical clocks along world lines. A clock here can be an atomic transition, a vibrating crystal, or any regular physical process. Time is what such processes measure, and the measurement depends on the geometry they inhabit. In cosmology, we often use cosmic time, defined by co-moving observers in an averaged homogeneous universe. That coordinate works extremely well after the earliest eras, where the fluid approximation holds. It lets us label slices of the universe by a shared age, as if the cosmos had a common heartbeat. It is a powerful simplification, and it matches observations with remarkable success. But coordinate time is not the same thing as physical time in every model. A coordinate can fail at a boundary even when physics continues in a different description. So we distinguish a chart from the manifold it describes, and we distinguish a parameter from an observable clock. When we ask what happened before, we may be asking for an extension of a coordinate that stops being defined. This distinction can feel abstract, so it helps to ground it visually. Imagine a map projection that stretches and tears near the poles, even though the Earth itself remains smooth. The failure is in the representation, not necessarily in the underlying object. In cosmology, a singularity can sometimes signal a breakdown of the classical description rather than a literal end of reality. The hard part is knowing which is which. Some models treat the Big Bang as a true beginning of time, not only of matter and radiation. In that case, before is like asking for a location north of the North Pole. The analogy is imperfect, yet it captures the logical structure of a boundary in a coordinate direction. If time begins, there is no earlier time within that model's domain. Other models replace the beginning with a transition, so time extends through in some form. A bounce model replaces a singularity with a minimum scale factor, then re-expansion.
In that case, before exists. But the physics near the bounce is not classical, and time's behavior can change. The word before survives, yet it may refer to a phase where familiar notions of distance and duration are transformed. An emergent time model goes further, treating time as a macroscopic parameter that appears only after certain conditions hold. In such pictures, fundamental equations may be written without a preferred time variable, and time arises as an effective description of correlations. That idea is difficult to test, but it addresses a genuine puzzle. If time is part of the universe, what does it mean to treat it as a background input? So the question, did time begin, is not a single yes or no across all theories. It is a question about what counts as time in the fundamental description, and whether that description has a boundary. It is also a question about what evidence could discriminate among these options. Without evidence, beginning risks becoming a matter of taste rather than a matter of physics. Here we tie back to the CMB wall and to the messengers we introduced earlier, because the universe does not give up its secrets easily. Photons cannot show us earlier than recombination, so we rely on fossils in statistics and on other weakly coupled signals. Primordial gravitational waves would be a messenger from extremely early times, if they exist at detectable levels. Their imprint could appear as a distinctive polarization pattern in the CMB, a faint swirl written into ancient light. A relic neutrino background would be earlier still, though detection remains far beyond current capability. Neutrinos decouple much earlier than photons, carrying information from a younger cosmos. Yet they are notoriously elusive, passing through matter almost without interaction. The irony is sharp. The cleaner the messenger, the harder it is to catch. But even if we had those messengers, time's beginning could remain conceptually subtle. A signal can tell us about conditions in an early phase, yet it may not answer whether time extends beyond that phase. Evidence can constrain models, but it cannot force a single metaphysical interpretation of before. So we keep the question scientific by asking what each model predicts that could be observed. Now we confront the arrow of time, because a beginning story is incomplete without it. Time feels directional, and physics must explain why the past and future are not interchangeable in experience. The equations of many fundamental laws are nearly time-symmetric, yet our lives are not. We remember yesterday, not tomorrow, and we watch eggs scramble but never unscramble. The core physical marker is entropy, a measure of how many microstates realize a macrostate. A macrostate is what we describe with coarse variables like temperature and pressure. A microstate is the detailed arrangement of particles and fields compatible with that description. The second law says entropy tends to increase in closed systems, giving time a statistical arrow. In cosmology, the arrow of time is tied to the early universe's remarkably low entropy. The early universe was hot and dense, yet it was also extraordinarily smooth and gravitationally special. For gravity, smoothness is low entropy, because clumped states like black holes have enormous entropy. So the early universe's uniformity is not only a geometric fact, it is a thermodynamic boundary condition. This point is easy to miss because hot and dense sounds like disorder. In ordinary gases, higher temperature often means higher entropy. Gravity changes the intuition because it makes clumping overwhelmingly probable over time. A smooth distribution of matter is like a carefully balanced pencil, improbable and delicate. The universe began balanced in that gravitational sense, and the arrow of time follows from that special start. This is a crucial link to the central question, and it raises the stakes. Explaining the beginning is not only explaining why there is something rather than nothing. It is also explaining why the universe began in a state that makes an arrow of time possible. If the initial state were generic, we would not expect a long, clean direction of increasing entropy. Inflation interacts with this issue in complicated ways, And we keep the claim careful rather than triumphant. Inflation can smooth and dilute, and it can set conditions for the observable patch.
It can also generate the tiny primordial fluctuations that later become galaxies, which is one of its great successes. But whether inflation explains the low entropy beginning or merely shifts the problem to pre-inflation conditions is debated. A model that generates our observed arrow must account for the specialness of the initial gravitational state. It must explain why the universe did not begin already maximally entropic, with space-time packed into black holes and chaotic curvature.
It must also respect what we observe. A cosmos that began simple enough to be described by a few parameters, then grew complex. The arrow is not an afterthought, it is part of the evidence. We can state the dilemma without taking sides, because the dilemma itself is the point. If the universe began in a low entropy state, we want a mechanism that makes that state natural or inevitable. If the universe is part of a larger multiverse or cyclic structure, we want to know why our region has such an arrow. If time begins, we want to know why the first moment is so ordered rather than maximally random. Now the chapter's haunting thread tightens into a single line, and we let it resonate. The quantum vacuum is not empty, and it can influence matter, forces, and possibly cosmic expansion. Vacuum energy can gravitate, yet its value is mysteriously small compared to naive quantum expectations. Quantum origin scenarios use vacuum-like states, but they still assume laws that define those states. So when we say, the universe came from nothing, we must ask what the word is hiding. Is it hiding a quantum vacuum with fields already present, plus mathematical rules already in force? Is it hiding a boundary where time is undefined, so before is not a location we failed to reach?
Or is it hiding a philosophical absolute nothing that physics cannot currently represent or test? This is the climax's final turn, and it is meant to be unsettling rather than tidy. The closer we get to the beginning, the more our everyday meanings of emptiness and before dissolve. We are left with evidence that the vacuum is real in its effects, and theories that extend the story past classical limits. We are also left with a quiet gap, where the deepest nothing may be a limit of scientific language. In that gap, questions become sharper rather than softer. If laws are required to define a vacuum, where do the laws come from? If space-time is required to define fields, can fields exist without space-time? If time is part of the universe, what does it mean for the universe to begin? These questions are not answers, but they are signposts marking where our current maps fade. We end by setting the next chapter's horizon, because the story cannot stop at the vacuum. To go further, we step into beyond Big Bang ideas, where the boundary becomes a larger structure. We consider cyclic universes, bouncers, and multiverses, where our universe may be one chapter in a longer book. And we ask what signatures could survive, because in cosmology, mystery only matters if it can be tested. We have rewound the universe to the edge where classical space-time stops behaving, and where our usual intuitions begin to fail. The central question returns in its hardest form. What, if anything, could have existed before the Big Bang, and what do scientists mean by nothing? Chapter 6 made one boundary unavoidable, and it is worth holding it in view as we move forward. Physics nothing usually means a vacuum state with fields, symmetries, and dynamical rules still operating in the background. Philosophical nothing would mean no space, no time, no laws, and no framework in which even possibility can be stated. The documentary ends by widening the frame, not by pretending the boundary disappears. First, we face the singularity problem directly, because it is the pivot point for every before story. In general relativity, the Big Bang singularity is not a place we can visit, or a moment we can film in any literal sense. It is a sign the equations are being pushed beyond their domain, because curvature scalars and densities diverge when we extrapolate too far. Historically, singularities were once treated as curiosities, but the Penrose-Hawking results made them difficult to ignore in realistic cosmologies.
If quantum gravity changes the rules at the Planck scale, around 10 to the minus 35 meters and 10 to the minus 43 seconds, the beginning might be a transition rather than an absolute start. This is the first major transition of the finale. We shift from a single origin point to possible pre-Big Bang phases. The question becomes which ideas are motivated and which can be tested. One family of proposals replaces the singularity with a bounce, trading an infinite spike for a finite turning point.
The universe contracts, reaches a minimum size, then expands again, like a compressed spring releasing. The Big Bang becomes a turning point in geometry, not the start of everything. And that shift changes what before can mean. Visually, the timeline no longer terminates. It narrows, pauses at a minimum, then opens outward into the hot, expanding phase. A big bounce is not one model, but a category. And that category hides many technical choices.
It needs a mechanism that prevents infinite density and curvature, because classical gravity alone tends to drive collapse toward a singularity. That mechanism usually comes from quantum effects, new matter components with unusual equations of state, or modified gravity terms that become important at high curvature. In plain language, something has to push back when gravity tries to crush space-time to a point. In many bounce pictures, contraction smooths the universe in a different way than inflation, and the difference matters for predictions. Some versions use an ekpyrotic phase with very stiff effective pressure, where the equation of state parameter is much larger than 1. That phase can suppress anisotropies and flatten the geometry before the bounce, because certain shear contributions dilute relative to the dominant stiff component. The visual language here is subtle. Instead of rapid stretching, the universe is ironed out during slow contraction, with wrinkles in geometry being damped rather than inflated away. Ekpyrotic ideas often draw inspiration from higher dimensional physics, and the imagery invites a careful kind of wonder. Our universe can be treated as a brain embedded in a larger space, with additional dimensions that are not directly visible at low energies. A collision or approach of brains can act like a trigger for a hot expanding phase, converting motion in the higher dimensional setup into heat and particles in the familiar four-dimensional world. Historically, these ideas grew alongside string-theoretic attempts to make gravity compatible with quantum principles, even though the cosmological details remain under active debate. At this level, we keep the claim modest, because the gap between mathematics and observation is real. Brain-inspired scenarios are motivated by attempts to unify forces and include gravity in a single, consistent framework. They are also speculative because the extra-dimensional dynamics are not directly observed, and many versions can be tuned to resemble more conventional early universe histories. The narrative value is not certainty, but the reminder that beginning might be a derived concept, not a primitive one. Bounce models must still explain the same data that inflation explains, and that is a high bar. They must generate the near-scale invariant, nearly Gaussian primordial fluctuations that seed galaxies and clusters. They must also match the observed phase coherence seen in CMB acoustic peaks, where the temperature and polarization patterns line up like harmonics in a resonant instrument. In other words, they must reproduce the early universe sound we observe, not merely avoid a singularity. They face additional challenges that are easy to state and difficult to solve in detail. A contracting universe tends to amplify anisotropies and inhomogeneities, because small directional differences can grow as the volume shrinks. A successful bounce must control that growth, and it must avoid instabilities that would cause the model to break before it reaches the turning point. Even if a bounce is mathematically allowed, it must be dynamically robust, not balanced on a knife edge. Some bounce models predict distinctive non-Gaussianity or a different tensor spectrum, and these are the kinds of differences that could matter observationally. Some predict a blue tilt for gravitational waves,
unlike many inflationary expectations that favor more power on large scales. These differences are where testability could live, if the signals are measurable, and if astrophysical foregrounds can be separated cleanly.
The question becomes practical as well as philosophical. Can our instruments hear the faintest echoes of a pre-expansion phase?
Now we widen the frame again, because inflation itself can imply a larger reality than a single hot beginning. Chapter 5 introduced eternal inflation as a possibility, not a conclusion, and we keep that careful posture here. In that picture, our hot Big Bang could be a local reheating event, like a pocket of hot plasma forming inside a much larger inflating background.
The camera, in effect, pulls back from one stage to a vast theater of stages.
Eternal inflation arises when quantum fluctuations compete with classical slow roll, and the competition never fully ends. In some regions, the inflaton rolls down its potential and inflation ends, allowing reheating and standard expansion to begin. In other regions, fluctuations kick the field upward, often enough that inflation continues, and space-time keeps expanding exponentially.
The result is not a single ending, but a self-reproducing process that can generate enormous diversity.
The result is a patchwork space-time with many bubble universes, though the word bubble is a metaphor, not a literal soap film. Each bubble is a region where inflation ended and a hot phase began, surrounded by regions still inflating too fast to thermalize.
Different bubbles can settle into different vacuum states, with different low-energy physics, because symmetry breaking and vacuum selection can vary across the landscape of possibilities. Visually, it is a mosaic of domains, each with its own internal arrow of time after reheating. This is the second major transition of the finale. The word beginning becomes local, and nothing becomes ambiguous. We must separate what is mathematically allowed from what is empirically anchored. The multiverse idea is motivated by some inflationary frameworks and by high-energy field theory, where multiple metastable vacua often appear. It is also controversial because of testability, which is not a minor technicality but the core of scientific credibility. If other bubbles are causally disconnected, they may leave no observable trace, and then the idea risks drifting from physics into uncheckable storytelling. The tension is sharp. The equations invite the picture, but the sky may refuse to confirm it. Some proposals search for indirect signs, and the search itself shapes what counts as evidence. A bubble collision might imprint a circular feature in the CMB, a subtle bruise in the microwave sky that would need careful statistical validation. A landscape of vacua might shift statistical expectations for parameters we measure, such as the cosmological constant or symmetry-breaking scales. Yet even these ideas must confront the possibility that the universe we see is simply one draw, and that selection effects can masquerade as explanation. But we keep the caution explicit, because cosmology has learned humility the hard way. Many such signatures are model-dependent, and can be mimicked by mundane systematics, foreground contamination, or incomplete understanding of astrophysical processes. A multiverse can become an explanation that fits anything, unless it makes sharp predictions that survive contact with data.
The discipline is not to reject bold ideas, but to demand that boldness eventually pays rent in measurements. The deepest difficulty is not only observational, and it is not solved by building a bigger telescope. It is also probabilistic and conceptual, because eternal inflation tends to produce infinite volumes and infinite numbers of events.
In that setting, defining probabilities can depend on how one regulates infinities, and different cutoffs can yield different answers.
The measure problem is a reminder that even counting can become ambiguous when the arena is unbounded. So the multiverse sits at an edge of science's usual method, balanced between derivation and verification. It is not pure fantasy, because it grows from equations people already use in inflationary model building.
It is also not established, because evidence has not forced us there, and because alternative early universe histories remain viable.
The honest stance is to treat it as a live hypothesis, not a settled worldview. Now we turn to the engine room behind every before story,
because the boundary is ultimately about the laws themselves. At the Planck scale, quantum mechanics and general relativity both matter, and neither can be ignored without distortion. We need a quantum theory of gravity to know whether space-time itself can begin, bounce, or emerge from something more fundamental. The question is not merely what happened first, but what happened even means when time may not be classical. Quantum gravity is not a single theory with one agreed form, and the fragmentation is part of the story. It is a research program with competing approaches and partial results, some rigorous and some provisional. The documentary treats it as an explanation for why the singularity may be a breakdown, not a literal event we should take at face value. When equations produce infinities, physics often interprets that as a signpost pointing toward missing degrees of freedom. Loop quantum cosmology is one approach applied to the universe as a whole, using ideas from loop quantum gravity in a symmetry-reduced setting. It suggests geometry is discrete at the smallest scales, with areas and volumes taking quantized values rather than forming a continuous spectrum. In some calculations, that discreteness produces an effective repulsion at high density, arising from quantum geometric corrections to the classical Friedmann equations. The visual metaphor is a fabric that cannot be compressed beyond a certain weave. At extreme density, the weave resists. In those scenarios, the classical singularity is replaced by a bounce, and the replacement is not just aesthetic. The scale factor reaches a minimum and re-expands, and the before is a prior contracting branch with its own thermodynamic and causal questions. Even then, the meaning of time can still be subtle, because quantum descriptions may not single out a unique classical clock near the bounce. The promise is not a final answer, but a concrete example of how quantum structure could change cosmic history. String theory takes a different route toward unification, and its imagery is both elegant and strange. It replaces point particles with extended objects, and it requires extra dimensions for mathematical consistency in many formulations. It aims to include gravity naturally, and it connects to gauge forces in a single framework through vibrational modes and symmetry structures. Historically, it rose from attempts to understand the strong force, then re-emerged as a candidate for quantum gravity when a graviton-like excitation appeared in its spectrum. String theory also suggests a landscape of possible vacuum states, and that suggestion has cosmological consequences. Different compactifications can yield different low-energy physics, because the shape and topology of the extra dimensions influence particle spectra and coupling constants. That landscape is one reason multiverse language appears in modern cosmology, because inflation could populate different vacua in different regions. The idea is powerful, but it also raises the uncomfortable question of whether uniqueness is a requirement for explanation. At this level, we keep the balance clear, because the subject can tempt overstatement. String theory is mathematically rich and unifies gravity with quantum principles in a way that has inspired deep tools across physics. It has not yet delivered unique, confirmed cosmological predictions that compel broad agreement. The frontier here is not only theory building, but the search for observational handles that could discriminate among frameworks. Unification matters because the early universe is a collider we cannot build, and the energies involved dwarf anything on Earth. At Planckian energies, separate forces may merge, and new degrees of freedom may appear, changing what counts as a particle or even a field. Without a unified framework, nothing claims risk being extrapolations of incomplete laws carried beyond their tested range. The deeper point is methodological. We must know the rules before we declare what the rules allow. Now we return to evidence, because the finale must stay disciplined even while it remains mysterious. The CMB remains our best fossil record of early conditions, a nearly uniform glow with tiny anisotropies at the level of tens of microkelvin. It is also a wall, because photons cannot show earlier than last scattering, when the plasma cooled enough for atoms to form and light to travel freely. Before that, the universe was opaque, and electromagnetic images simply do not exist.
So we look for messengers that cross the wall, and gravity is the most promising candidate. Primordial gravitational waves would carry information from extremely early times because they interact weakly and propagate almost unhindered.
Their imprint could appear as B-mode polarization, a faint, swirling pattern in the CMB that must be separated from dust emission and gravitational lensing. The observational challenge is almost poetic. We are trying to detect a whisper beneath a chorus of nearer, louder signals. Improved CMB polarization maps can tighten constraints on tensor modes and non-Gaussianity, and those constraints translate directly into early universe model space. They can also refine the reionization history and lensing reconstruction, which in turn improves our ability to subtract lensing-induced B-modes. Each improvement shrinks the space of viable early universe models, not by rhetoric, but by numbers. In the best case, a detection would not just confirm a mechanism, but measure its energy scale. Large-scale structure surveys add a second fossil record, written not in photons, but in the distribution of matter.
Galaxy clustering and weak lensing map how primordial perturbations grew into the cosmic web, with filaments, voids, and clusters tracing the initial conditions. They can test scale dependence, running, and departures from simple Gaussian initial conditions, especially when combined with CMB priors. Visually, the universe becomes a three-dimensional map of ancient ripples, stretched across billions of light years.
We also acknowledge unresolved tensions without overpromising, because anomalies can be either hints or mirages.
The lithium problem remains a mismatch between predicted and observed primordial lithium, relative to the otherwise impressive success of Big Bang nucleosynthesis. It may be astrophysical systematics, such as stellar depletion or modeling uncertainties, or it may hint at new early universe physics.
The responsible posture is to keep it on the table, while resisting the urge to build castles on a single discrepancy. Any pre-Big Bang scenario must respect these constraints, and constraints are what turns speculation into science. It must reproduce the success of nucleosynthesis and the CMB spectrum, including the precise ratios of light elements and the angular power spectrum peaks. It must also avoid adding free parameters that only hide ignorance, because flexibility without prediction is not explanatory power.
The goal is not merely to tell a story that could be true, but to tell a story that could be wrong. This is the third major transition of the finale. We move from candidate histories to the meaning of the words. Nothing before the Big Bang can mean several different things, and mixing them creates false certainty.
Option 1 is classical, and it is the simplest to state, though not always the easiest to accept.
Nothing before can mean no classical space-time exists earlier than the Big Bang, so there is no earlier time coordinate to refer to. In that reading, before is undefined, because time is part of the system, not an external container. The question then becomes like asking, what is north of the North Pole? Grammatically clear, but physically misplaced.
Option 2 is quantum, and it is often what physicists mean in practice when they say, nothing.
Nothing can mean a quantum vacuum state, the lowest energy configuration of fields consistent with the laws. That vacuum is not empty in the philosophical sense, because it contains structure, correlations, and fluctuations that can be amplified by cosmic dynamics. Even in ordinary laboratory physics, vacuum fluctuations have measurable consequences, reminding us that empty is rarely truly empty.
Option 3 is mathematical, and it shifts the emphasis from time to rules.
Nothing can mean a boundary condition, like a no-boundary proposal or a specific initial quantum state defined by a path integral over geometries. The universe is then described by a rule that selects histories, not by a prior time in which something waited to begin. In this view, the deepest question is not what came first, but why this class of histories is realized.
Option 4 is philosophical, and it is the hardest to translate into equations without changing its meaning.
Nothing can mean absolute non-being, with no laws and no possibilities, not even a space of states. Physics cannot model that directly, because physics is a language of laws and states, and the act of modeling already assumes structure. The boundary here is not only empirical but conceptual, marking the edge of what scientific description can coherently address.
These meanings are not interchangeable, and the documentary keeps returning to that point for a reason. When a model says, "from nothing," it usually means from a vacuum or from a boundary condition, not from absolute non-being. The documentary's job is to keep that distinction visible, because clarity is part of the mystery rather than the enemy of it. If we want to be astonished by the universe, we should first be precise about what we are claiming. Now we bring the story back to the opening hook, and we let the visuals carry some of the weight. If you rewind past every galaxy, past every atom, past light itself, you do not reach a familiar emptiness. You reach the point where the concepts of space, time, and vacuum must be defined carefully, because they may not be fundamental. The screen can fade from star fields to a smooth thermal glow, then to abstract geometry, then to a quiet blankness that is not quite nothing. Cyclic and bounce cosmologies offer one kind of answer, and they do so by changing the meaning of origin. They say there was a prior phase, and the Big Bang was a transition, perhaps governed by new physics at extreme density. Eternal inflation offers another kind of answer, and it does so by multiplying beginnings. It says our beginning may be one event among many, inside a larger inflating space-time, with reheating events scattered like sparks. Quantum gravity offers a deeper reframing, and it is the most radical without being purely speculative. It suggests space-time may be emergent, discrete, or fundamentally different near the Planck scale, where classical geometry may dissolve into quantum structure. In that case, before might refer to a regime where time is not yet classical, and where our best language is probabilistic rather than narrative. The question becomes whether the universe had a first moment, or whether moment is an approximation that eventually breaks. We do not resolve these possibilities into a single winner, because the evidence does not yet force one story. The honest conclusion is that the boundary is real, and the theories are attempts to describe what lies beyond it. Some are motivated by the need to cure singularities, some by the internal logic of inflation, and some by the demand for quantum consistency. What unites them is not certainty, but the insistence that even the earliest universe should be intelligible in principle. Still, the boundary is not a failure, and it is not an admission that the cosmos is ultimately unknowable. Every galaxy, every atom, and every pattern in the CMB suggests lawful behavior deep into the early universe, with regularities that persist across immense scales. The laws may operate even when space is not yet a smooth stage, and when geometry itself may be a derived quantity. The more we learn, the more the universe looks like a system with structure all the way down, though we do not yet know what down finally means. Our ignorance is part of the narrative, not an embarrassment, and it is also a map of where progress can happen. The Big Bang is a well-tested description of an early hot phase, supported by expansion, nucleosynthesis, and the microwave background. The question of what preceded it is where physics becomes frontier science, because it forces us to test the limits of our most successful theories. The mystery is not a gap to be papered over, but a boundary to be approached with better models and better data. The finale ends with a quieter claim, because quiet claims are often the most durable. Nothing is not a final answer in cosmology. It is a marker for where our descriptions change, and where our tests become harder, and where language itself must be handled with care. When someone says the universe came from nothing, the first question is not whether it is profound, but what definition of nothing they are using. When we ask what existed before everything, we discover the edges of thought and measurement, and we discover how much depends on definitions. We also discover the power of models that turn mystery into constrained possibilities, where even uncertainty has shape. The question of nothing is a mirror, and it reflects how far explanation can go, before it must either deepen its foundations or admit the limits of what can be asked. We rewound the cosmos the only honest way, from the evidence outward, and watched space itself stretch rather than explode into darkness. The cosmic microwave background became our oldest photograph, its faint temperature ripples and polarization patterns telling us what the young universe contained, how smooth it was, and how structure began. But as we pushed earlier than that first light, the story turned from photons to equations, and the equations led us to a boundary where general relativity stopped speaking clearly. At that edge, nothing split into meanings we had to keep separate, because swapping them quietly changes the question itself. Philosophical nothing is absolute non-being, with no space, time, laws, or even a place for truth to stand. Physical nothing is a quantum vacuum, a lowest energy state with fields, fluctuations, and a gravitational presence that can shape space-time. The Big Bang model, tested by expansion, light element abundances, and the CMB's detailed map, carries us far back, yet it does not guarantee a literal beginning. The singularity we meet when extrapolating backward may be a genuine origin, or it may be a warning light that our classical description has been pushed beyond its jurisdiction. Inflation entered as a proposed bridge across that warning, explaining the universe's flatness and smoothness while turning quantum noise into the seeds of galaxies. Yet inflation also complicates origins, because it can erase traces of any earlier phase, even as it predicts subtle statistical fingerprints we still hunt for. Meanwhile, the loose ends remain instructive rather than embarrassing, from the lithium mismatch to the vacuum energy catastrophe, because they mark where our models are strained and where new physics might hide. Past the CMB wall, we are not blind, but we are limited, and we learn to listen for other messengers. Relic neutrinos and primordial gravitational waves could carry information from earlier times, and CMB B modes could reveal whether inflation happened and how violently space-time itself once rang. Beyond that, cyclic bounces, emergent time, and multiverse ideas expand the menu of possibilities, but they also raise the price of belief, because in cosmology, imagination must eventually pay rent in observable consequences. So what was it that exploded? And what was there to do the exploding if the universe came from nothing? The most careful answer is that the Big Bang was not a blast into emptiness, and nothing was never a simple void, but a boundary where our everyday meaning of before dissolves, and our physical meaning of vacuum still carries structure and rules. If time is part of what began, then before the Big Bang may be like asking what lies north of the North Pole. Not a refusal to wonder, but a warning about the map we are using. And if some deeper theory makes time emergent, then before may be replaced by something colder and stranger, a prior phase, a transition, or a timeless description whose traces survive only as patterns in the sky. In that light, universe from nothing is not a final explanation, but a claim about which assumptions are being smuggled in. Fields, laws, and a vacuum state are already a kind of something. The real question becomes sharper and more scientific because it asks what is truly required for a universe to exist, and what evidence could ever tell us we are right. We do not yet know whether the singularity is a birth certificate or a signpost to quantum gravity, but we can say where certainty ends and where disciplined inference begins. In the end, nothing is less an emptiness than a mirror held to the limits of language and to the limits of physics itself. The closer we approach the beginning, the more space, time, and causation stop behaving like the stage we stand on and start behaving like actors we must explain. What survives that approach is not a tidy answer, but a kind of clarity. Some questions are category errors, some are testable, and some are mysteries with edges we can measure. The universe may have emerged from a vacuum, from a bounce, from an inflating patch of space-time, or from a framework where time is not fundamental at all. Yet whatever the deeper story is, it left a signature, and our job is to learn how to read it without confusing poetry for proof. Perhaps the most unsettling possibility is not that the universe came from nothing, but that nothing is the name we give to the boundary where explanation becomes possible at all. And perhaps the most hopeful one
is that boundaries move slowly as instruments improve, as theories sharpen, and as we keep asking the question with enough precision to let nature answer.
If you want to follow the mystery forward, watch the next generation of CMB polarization maps, gravitational wave searches, and neutrino experiments. Because the earliest universe may still be speaking, and we are finally building ears to hear it.